Hello there, and welcome to Science for Sleep, a small quiet corner where curiosity winds down at a gentle pace and wonder feels like something you can rest beside. Tonight we're settling into a calm drift through one of the most humbling ideas we humans ever tried to grasp, the scale of the universe. Not as a number, not as a chart, but as a feeling you can lean into slowly. When we talk about the cosmos, it's easy to picture swirling galaxies and glowing stars scattered like distant lanterns. But the moment we ask where Earth fits into all of that, something soft and slightly dizzying happens in the mind. Our home becomes small, not in a frightening way, but in a way that nudges you toward an easier breath. Like realizing you've been holding your shoulders too high all day and only just now let them relax. Before we wander outward, I'd love to know something simple. Where are you listening from tonight? Not just the country or the city, but what it feels like around you. Are you curled under blankets, lights turned down low? Are you winding down after a long stretch of tasks and noise? Maybe you're listening with headphones while the rest of your home stays quiet, or maybe this is playing softly in the background as you close your eyes. However you're here, I'm glad you made it into this moment, and since we're about to explore distances that stretch farther than comfort would normally allow, feel free to let the weight of the day soften a bit. No need to hold on to any tension while the universe unfolds around you. If you find this kind of slow exploration soothing, or simply a peaceful break from everything else life might ask of you, I'd be grateful if you gave this a like or maybe subscribed. It helps this little sleepy community reach more people who might need a pause, a quiet breath, or just a space to drift for a while. But don't worry about that too much right now. You're here, and that's enough. When we begin to think about the scale of the universe, there's a strange mixture of comfort and uncertainty that arises. Not the dramatic sort, but the gentle kind. The kind that reminds you how much exists beyond commutes, emails, grocery lists, and everything else we pile into a day. We often say Earth is small, and compared to the whole cosmos, that's undeniably true. But the feeling of that smallness isn't about insignificance. It's more about perspective. The kind that sneaks up on you when you look at the sky too long on a clear night and realize those tiny points of light are impossibly far, yet somehow familiar. What makes the scale of the universe such a soothing subject for a sleepy evening is the slow way it unfolds. There's no rush in cosmic distances, no urgency in planetary motions. Everything out there moves on timescales that make our daily concerns look like quick ripples on a calm lake. Even the fastest stars and the brightest galaxies follow rhythms that stretch far beyond a lifetime, and there's something strangely calming about that. A reminder that the universe isn't demanding anything from you. It simply exists, quietly, steadily, with no expectation that you keep up with its pace. Earth sits in the middle of all this as a small round speck carrying oceans, mountains, forests, cities, and billions of people who each have their own private timeline of memories and hopes. When we talk about how small our planet truly is, it's not meant as a diminishment. It's more like noticing how a single candle glows in a wide room. The glow doesn't shrink just because the room is large. If anything, the contrast makes it easier to appreciate the warmth of the flame. Earth is like that. A bright patch of life in a cosmos mostly quiet and cold. That contrast doesn't make us feel lost. It makes everything familiar feel more precious. Before we drift too far outward, it helps to settle into the simplest starting point, the view from where you are. Maybe you're inside, surrounded by textures and objects that make up your personal world. Maybe you're near a window where night has already arrived, or perhaps the sun is still lingering depending on your corner of the globe. Wherever you are, the distance from you to the nearest tree or building or streetlight is tiny compared to the vastness we're about to explore. Yet it feels real, close, immediate. Our senses are built for short ranges. We understand rooms, we understand cities, we can imagine continents. But the cosmos stretches so far beyond our built-in sense of scale that we need to shift gently into a different kind of awareness to even begin to picture it. As we start moving outward, It's worth remembering that Earth is the only place we know of where someone can sit comfortably and think about the universe at all. The only place where air fills lungs, where water flows across the ground, where warmth and light collaborate to support the entire story of life. That makes Earth feel larger in a way, as if its importance expands even as its physical size shrinks in comparison to everything else. A small home can still hold a whole life. A small world can still hold countless stories, connections, and moments that give meaning to the space inside it. Thinking about size on this scale brings up a simple question. How do we even measure something so large when our minds are anchored to the everyday? It's one thing to picture a mountain or an ocean, but entirely another to imagine the gap between planets or the emptiness surrounding stars. The numbers are so big they slip through the mind before we even have a chance to grasp them. That's why we ease into them slowly, step by step, without forcing the mind to stretch too far at once. The universe is patient. There's no need to rush. When astronomers talk about distances, they often use light itself as the ruler. Not because it's familiar, but because it's constant. Light moves steadily, without pause, covering enormous stretches of space in a way that feels almost effortless. Even then, we rely on simplifications because the actual scale is too big to hold all at once. But tonight we're not racing toward numbers or calculations. We're drifting through the feeling of scale, letting the immensity of the cosmos wash over us in a slow, steady flow. It's almost funny to think that when you step outside on a clear night and look up, the universe appears incredibly close. The stars seem pinned just beyond reach, as if a short climb might get you there. But in reality, every single point of light is staggeringly far away, so far that even the nearest star beyond the sun is separated from us by a distance so immense it takes light more than 4 years to cross it. And that's just the beginning. That's barely outside our cosmic driveway. The true scale of the universe isn't something you grasp all at once. It's something you ease into, like walking slowly from a small room into a field that stretches farther than the eye can see. First, you notice what's near, then you begin to sense what's a little beyond that. Eventually, the horizon expands so far in your imagination that you realize the field never truly ends. It just keeps going, patiently, quietly. And as we settle into this gentle exploration together, the goal isn't to overwhelm the mind, but to let it stretch just enough to feel the awe without the strain. Earth will seem smaller the farther we go, but not in a way that makes it feel unimportant. More in a way that highlights how remarkable it is that life appeared on this little sphere in the first place. A warm oasis tucked into the emptiness, holding everything familiar within a thin shell of air and clouds. You don't need to hold the whole universe in your thoughts at once. You just need to follow the slow widening of perspective. Bit by bit, the distances will make sense in their own calm way. The stars will feel farther, the galaxies will drift into view, and Earth will settle gently into its place as a small but extraordinary home, floating in an expanse that doesn't rush, doesn't demand, and doesn't end abruptly. It continues quietly beyond anything we can touch. So as we ease forward, imagine the simplest picture. You, somewhere on this round blue world, listening to a soft voice describing a universe too large to measure in any ordinary way. And as that picture settles, allow the edges of your daily world to loosen a little. The universe is spacious. When we begin to picture where we live in the universe, it helps to start with the most familiar view, the one we rarely stop to appreciate because it's always beneath our feet or above our heads. Earth feels enormous when we're moving through our daily routines. Travelling even a single country can take hours. Flying across an ocean can take most of a day. Climbing a mountain, crossing a desert, or sailing across a sea can make the planet seem too large to ever fully grasp. And yet, the moment we try to understand the universe around us, this same world becomes something much smaller, almost delicate in scale. Not fragile in a fearful way, but contained. a place with boundaries that feel comforting when we notice them closely. Most of us rarely think about Earth's size beyond the rough image of a globe in a classroom or a map spread across a desk. Those flattened maps distort almost everything, stretching continents where they shouldn't be stretched, shrinking others until they appear far less significant than they truly are. But if you imagine Earth as it actually is, a round world suspended in a dark expanse, the picture becomes more honest. You can picture the oceans covering most of its surface, the continents resting like islands in a much larger sea, and the atmosphere wrapped around it like a thin protective layer that holds warmth, air, clouds, and weather in place. It becomes easier to picture Earth not as the centre of anything, but as a place floating gently within a much larger environment. When astronauts describe seeing Earth from space for the first time, they often mention how surprising it is to realise how small the planet looks from even a short distance above it. They talk about seeing no borders, no lines between nations, no sense of human division, just one continuous sphere, and they describe the thinness of the atmosphere in a way that catches people off guard. From the ground, the sky seems endless. From orbit, it looks like a narrow band of blue pressed tightly against the curve of the planet. In some ways, the more distance you have, the more interconnected everything becomes. The sky that looks boundless from the ground becomes something you could almost pinch between your fingers if you were looking at it through a spacecraft window. The view from space gives us a useful starting point, not because everyone can experience it, but because it reveals something our daily lives keep hidden. Earth isn't as wide as it feels when we're inside it. The scale we experience while standing on the surface is entirely different from the scale seen from above. When we're walking down a street, 1,000 metres feels like a distance. When we're looking at a globe, 1,000 kilometres barely makes a mark. And when we take a step back into the larger cosmic picture, the entire planet becomes something that could fit comfortably beneath a fingertip on an imaginary map of the universe. Still, even when we understand that Earth is small compared to the larger cosmos, the size of our home is not meaningless. The distance around Earth at the equator is about 40,000 kilometres, which means if you could somehow walk without resting or slowing, and if you could step across oceans as easily as sidewalks, it would take months to complete a single loop. And yet light, the fastest thing we know, can travel around Earth more than 7 times in 1 second. When you think about it that way, the planet starts to feel small in a way that's both surprising and strangely grounding. We live on a world that's vast enough to hold every environment we know, yet compact enough for light to wrap around it repeatedly before a clock ticks once. This shift in perspective is where the journey outward begins. You might picture yourself standing somewhere familiar, maybe on a quiet street or near a window, where the day has already begun to soften. You imagine rising gently upward. At first, everything looks the same. You can see rooftops, trees, roads, perhaps the faint glow of lights turning on for the evening. A bit higher and you start to see patterns. A river that curves through a city. A coastline that outlines the edge of a country. The shapes become clearer even as the small details fade. Rise higher still and something interesting happens. People, cars, buildings, everything that feels busy and urgent from the ground turns quiet and still. Not because it stops existing, but because the scale you're viewing it from has pulled you farther away from those details. Eventually, if you keep imagining yourself drifting upward, the land masses begin to show their full outlines. Continents come into view. Oceans take shape as vast stretches of blue. White clouds swirl across the atmosphere in slow patterns that unfold gradually. And before long, you begin seeing the world the way astronauts describe it. A sphere with soft blues, greens and browns, turning steadily beneath a thin layer of air. It's only at this height that the phrase tiny blue shore makes sense. Earth is not just a planet. It is a shoreline at the edge of a larger sea. The sea in this case is the universe itself, stretching endlessly in every direction. Thinking about Earth from this vantage point adds a quiet calm to the mind. The speed at which life moves on the surface becomes less pressing. The noise of everyday tasks fades. The scale of the world shifts from overwhelming to manageable. Knowing that everything familiar is gathered together on this small, round place doesn't make life less meaningful. It simply puts it into a context that feels more spacious. When we move further outward in our thoughts, Earth begins to shrink visually. At first it becomes a sphere that could fit in the palm of your hand. A bit farther, and it looks like a marble. Farther still, and it becomes a dot. At some distance, it becomes invisible altogether. But even when it disappears from view, it's still there. It's still holding all the complexity of life, all the stories, all the individuals experiencing their own quiet evenings or early mornings. The fact that Earth can become invisible long before the universe ends says more about the scale of the cosmos than anything else. Our home is not small because it's insignificant. It's small because the universe is overwhelmingly large. Yet the view from our tiny shore is where everything begins. Every observation, every measurement, every imaginative stretch toward the stars starts here. This round planet provides the only window we have into the rest of the cosmos. Every image we've captured of distant galaxies, every calculation of stellar distances, every interpretation of cosmic evolution, all of it has been done from this one location. That gives Earth a kind of anchoring presence that doesn't change even when we acknowledge its small physical size. If you picture explorers mapping a vast ocean, their position on a single island doesn't diminish the value of the work they do. The island becomes the starting point for the journey. Earth works the same way. Something else becomes clear the more you think about this. The universe is so enormous, so stretched beyond anything familiar, that the human mind can't hold it all in focus at once. But Earth, being small by comparison, is something we can grasp. And that grasp is what allows us to reach outward, slowly, carefully, until the boundaries we thought were limiting begin to expand in gentle steps. The view from our little shore becomes the perspective from which we can understand everything beyond it. Even as we think about Earth shrinking in size the farther we imagine ourselves drifting outward, there's an interesting shift that takes place. The meaning of the world doesn't shrink with it. The farther we step back, the more we see how much is contained in that single small sphere. Not just landscapes and oceans, but entire histories, cultures, languages, families, and all the quiet moments lived by individuals. A planet can be physically small while emotionally vast, and that contrast is part of what makes the journey outward so intriguing. We're not just measuring distances, we're measuring perspective. You might picture Earth again now in your mind. A round world with continents resting like shapes you could trace with a fingertip. Clouds drifting lazily over oceans, and a thin blue line of atmosphere marking the boundary between air and space. That line holds everything we breathe. Without it, the world would be silent. But because it exists, the planet carries voices, wind, weather, and life itself. It may be small compared to what surrounds it, but it is complete. The smallest shell can hold a full world inside it when seen from the right angle. The more we look at Earth from this imagined vantage point, the more it becomes clear that our tiny shore is not defined by what it lacks, but by what it contains. And as we ease our way outward from this point, the scale around us will grow so rapidly that we'll need this anchor to keep everything grounded. The universe won't get smaller as we explore it. Our understanding will simply adjust in ways that make the distances feel less intimidating. When we begin comparing Earth to things beyond it, a curious shift happens almost immediately. The planet that feels impossibly wide when we're trying to cross a continent or fly from one hemisphere to another begins to seem compact once we place it beside the objects orbiting near us. But before we rush into comparing its size to the Sun or the other planets, it helps to understand Earth in terms that don't rely solely on distance or measurement. We live here. Everything familiar fits onto this single sphere. That gives the world a kind of emotional scale we rarely acknowledge. We feel its size not through numbers but through experience. Think about how big Earth feels when you're driving for hours and the road keeps going. The landscape changes slowly. Towns appear and disappear. The terrain shifts in ways that make the world feel almost endless. A single day of travel barely touches a fraction of the planet. Even a long flight often reveals that there's still so much more you haven't reached. From that perspective, Earth seems enormous, and for most of human history it was. Generations lived and died without ever travelling more than a small portion of it. Entire civilizations rose and fell without knowing what lay beyond distant oceans. But the moment we look at Earth, not as a collection of journeys or experiences, but as an object in space, its size takes on a very different meaning. The planet is about 12,142 kilometres across. A number like that is more than most of us can picture comfortably. To put it in perspective, if you could shrink Earth down to the size of a basketball, an airplane flying just above its surface would be thinner than a sheet of paper. That's how thin the atmosphere is compared to the size of the planet. The tallest mountains become tiny bumps. The deepest trenches turn into faint scratches. Everything that feels vast and towering in our daily lives becomes something you might miss if you didn't look carefully. Yet describing Earth this way doesn't quite capture the feeling of it. Because while the planet is physically small compared to the universe, the way we experience it gives it emotional weight. Earth is where every memory you've ever had has taken place, whether you were aware of the sky or not. The streets, rooms, parks, schools, workplaces, forests and coastlines you've known all sit on this planet's surface. Your ideas, fears, hopes, frustrations, routines, and the quiet moments you never told anyone about all unfolded on this single world. That sense of familiarity makes Earth feel substantial, even though its actual size is modest when viewed from a cosmic perspective. A useful way to understand this contrast is to imagine standing at the ocean's edge. When the water stretches out to the horizon, it can feel nearly infinite. You know it isn't, but your senses tell a different story. The horizon hides everything beyond it. You can't see where the ocean ends or where another continent begins. The world feels enormous because your view is limited. Our perception of Earth's size works the same way. We experience it through fragments, small pieces that trickle into our senses moment by moment. We rarely see the whole, so we fill the missing pieces with assumptions about vastness. Now imagine stepping back, not physically but mentally, until you picture the entire planet. You see the oceans covering most of the surface. You see the continents laid out in shapes you could trace with a finger. And you notice how the world fits comfortably inside your mind's eye, a clear and complete image. The emotional scale of the world shifts slightly. What once felt overwhelmingly large becomes something you can hold as a single idea. That shift isn't about numbers, it's about perspective. To understand Earth's size more clearly, imagine trying to drive around its entire circumference. If you travel by car at highway speed without ever stopping, switching drivers every few hours like some determined relay team, the trip would still take days. But light, which moves faster than anything else known, circles the Earth more than 7 times every second. In the time it takes for you to blink, light has already completed multiple laps. That difference in speed is one of the first hints that Earth is not as large as it feels while we live on it. The planet's width becomes something that even a beam of light can cross effortlessly in an instant. The idea becomes even more striking when we compare Earth to the Sun, but we're not quite ready for that step yet. Before moving outward, it's worth lingering a little longer on the emotional and perceptual size of the world. When you stand in a crowded city, the tall buildings, busy streets, and dense surroundings make the world seem compressed. Everything feels immediate and close. But when you stand in an open field or at the edge of a quiet lake, the spaciousness around you gives your mind room to expand. Earth's perceived size shifts depending on context. Our senses don't measure kilometres, they measure experience. If you've ever looked at a world map and felt strangely small, that feeling comes from seeing continents arranged in a way that reveals their true relationships. North America sits beside the Atlantic, which touches the edges of Europe and Africa, which connect to Asia, which leads to the Pacific, which loops back to North America. The world becomes a continuous loop rather than a collection of separate regions, and once you see it that way, it becomes easier to imagine Earth not as an endless sprawl, but as a single connected place. Despite this, we often forget that the surface of Earth is thin. If the planet were an apple, the atmosphere would be thinner than its skin. The crust where we live would be even thinner than that. The entire biosphere, the layer where all life exists, is like a faint smear on the surface. Everything we know, everything that breathes, grows, eats, sleeps and thinks exists within a narrow band that barely extends into the planet or the sky. That thinness adds another layer to the idea of Earth's size. It's not a deep world, but a broad one. Life spreads out across it, filling the surface with movement and meaning. Thinking about Earth this way also reveals a subtle truth. The world feels large to us because we move so slowly compared to the distances involved. Walking, driving, even flying, all are slow on a planetary scale. If humans could suddenly move at a significant fraction of the speed of light, Earth would feel no larger than a neighbourhood. The fact that it takes time to travel across continents is what gives the world its sense of size. The slowness of our movement stretches the planet in our perception, giving it depth it doesn't physically possess. Another way to look at Earth's size is to consider just how much of it we personally experience. A single human life occupies only a tiny fraction of the planet's surface. Most people never travel more than a handful of countries. Even those who spend their lives exploring still cover only a small portion of the globe. The world is filled with landscapes we will never walk across, forests we will never see, mountains we will never climb, and oceans we will never cross. This limited exposure makes Earth feel constantly new. There is always more of it than we personally encounter, but the moment we step outside the boundary of personal experience and view Earth factually rather than emotionally, the planet becomes compact. Astronomers sometimes say that if Earth were the size of a standard classroom globe, the Moon would be a small ball sitting several feet away. The Sun would be the size of a very large sphere placed more than 100 meters distant, and Earth itself would be a dot compared to other objects in the solar system. The world that holds everything familiar becomes something small enough to disappear quickly once you begin moving outward in scale. Yet despite the world's modest physical size, there is something uniquely comforting about its dimensions. Earth is large enough to contain endless variety, but small enough to be understood as a whole. It is a world where deserts, tundras, jungles, plains, cities, and oceans coexist in ways that feel natural once you see the planet as a complete sphere. The size allows for difference without disconnect. You can travel far enough to find environments completely unlike your own, but not so far that the world becomes disjointed. There's also a psychological aspect to Earth's size that people rarely consider. Because the world is round, you can travel in any direction and eventually return to the place you began. There are no edges, no ends. The finiteness of the planet provides a subtle sense of containment, which the universe as a whole does not. When thinking about the cosmos, the absence of edges can feel overwhelming. But Earth's boundaries offer a kind of mental safety. It's a finite place with defined limits, making it understandable even when the universe is not. All of this comes together to create a strange duality. Earth is small physically but enormous experientially. It is limited geographically but abundant emotionally. It is a tiny planet orbiting a medium-sized star in a galaxy full of billions of others, yet it feels expansive because we live inside its details. When you think about how small Earth truly is, you're not diminishing its significance. You're making room for a clearer understanding of everything that surrounds it. It can be surprising how much perspective shifts the moment we stop thinking only about Earth itself, and instead consider the space just beyond it. The world feels fairly self-contained while we live on its surface. But as soon as we look toward the moon, the scale of everything begins to stretch. The moon seems close when we see it rising over rooftops or hanging above a quiet road at night. Its surface looks almost touchable, as if a long ladder or a determined climb could take us there. But that impression dissolves once we learn how far away it actually sits. The distance is gentle in the sense that the moon is our nearest celestial neighbour, but it is also enormous compared to anything we move through in our daily lives. Most people have heard the number before. Roughly 384,000 kilometres separate Earth from the moon. Hearing it is one thing. Understanding it is something else entirely. When you look at the moon from the ground, it appears the size of a coin in the sky. The fact that something so small-looking is actually a world thousands of kilometres wide tells you immediately that your senses are not equipped to judge cosmic distances. The light from the moon makes it feel present, almost companion-like, but the empty space between us and that cratered world is vast enough that it took humans thousands of years just to imagine crossing it, and even longer to actually succeed. One way to feel the scale more clearly is to imagine Earth and the moon sitting on a table, reduced in size but keeping their proportions. If Earth were a basketball, the moon would be roughly the size of a lemon, and that lemon would sit several meters away. Not next to the basketball, not within easy reach, far enough that you'd instinctively take a few steps to close the distance. This simple model already reveals something important. For all appearances, Earth and the moon are not neighbours, in the sense that two houses on a street are neighbours. They are separated by a gap large enough to fit every other planet in the solar system between them, with space to spare. That alone shifts the way we think about Earth's place in its own little corner of the universe. The space between Earth and the moon is not empty in a dramatic or intimidating sense. It's simply open, quiet, and vast. No air, no weather, no sound, no wind. Just a gradual thinning of Earth's influence as distance increases. The atmosphere fades long before that halfway point, turning from breathable air to thinner layers, and eventually to nothing at all. Gravity weakens slowly but never vanishes. Light travels effortlessly across the gap, making the moon appear closer than it is. But for humans, that space remains enormous. Nothing in our everyday movement compares to it. A long drive, a cross-country flight, even a wide ocean crossing. None of these experiences prepare us to intuitively grasp what 384,000 kilometres means. This gap also reveals something subtle about Earth's size. The moon is much smaller than Earth, yet from a distance it commands attention. It is bright enough to cast shadows, steady enough in its orbit to guide ancient calendars, and close enough to influence tides across the planet. The fact that something so capable sits so far away highlights how small Earth becomes in spatial terms when we place it in cosmic context. The moon's distance dwarfs any place on Earth. You could travel from one side of the world to the other dozens of times and still not cover the space between Earth and its companion. When astronauts travelled to the moon, they described an experience that underscored just how wide the distance feels once you're making the journey. As their spacecraft drifted farther from Earth, the planet began to shrink. At first, it looked like a giant curved horizon through the window. Later, it became a round sphere suspended in blackness, and eventually it became something they could cover with a thumb held at arm's length. The world that had always felt undeniably large became suddenly small. Not insignificant, just contained. Seeing Earth from that distance changed the way many astronauts thought about home, borders, conflict, and the everyday rush that fills life on the surface. When a planet can be covered by a thumb, arguments and worries seem slightly less rooted than they once appeared. The moon has a similar effect when viewed from Earth, even if we're not aware of it. It becomes a reference point for distance. We know it is far away, but still visibly present. That combination makes it a stepping stone in our mental journey outward. The moon is not so far that it disappears from view, nor is it so close that it feels within easy reach. It occupies a middle ground, the first true landmark beyond Earth's surface. Once you consider it properly, the scale of the universe begins to open up in a steady, manageable way. The distance also matters because of what lies within it. There is no physical structure connecting Earth to the Moon, no bridge, no faint trail of matter, no tunnel. Just space. That emptiness might sound eerie, but in this context it becomes soothing. It suggests the universe doesn't rush, it doesn't crowd. It offers room for objects to coexist without colliding. Earth and the Moon orbit one another in a quiet cosmic dance across a space filled with nothing but the soft pull of gravity. That calmness is something we rarely associate with distance because, in human terms, long distances often come with effort, time, or strain. In space, distance simply exists. No struggle, no hurry. Just the quiet separation of celestial bodies. To get a better sense of the Moon's true scale relative to Earth, think again of the basketball and the lemon. The Moon is about 1/4 the width of Earth. That makes it large compared to many other moons in our solar system. In fact, relative to its planet, our Moon is unusually big. This gives Earth-Moon system a distinctive character. The Moon influences tides, stabilizes Earth's rotation, and affects the length of our days in ways that many people never think about. Without the Moon, Earth would wobble more chaotically. Seasons might shift unpredictably. Climate would be less stable. In that sense, the Moon is not just a distant sphere. It is part of Earth's identity, even if it sits far outside our immediate reach. But even knowing this, the distance remains difficult to feel intuitively. The Moon seems reachable when we see photographs of astronauts standing on its surface, because the human figures add familiarity. Their presence makes the landscape seem tangible. But consider how long it actually takes to get there. The Apollo spacecraft needed roughly 3 days to cross the gap. 3 days of drifting through blackness, with Earth shrinking behind and the Moon growing slowly in the window. Imagine looking out and seeing both objects, realizing that you've left one world but haven't yet arrived at another. That space in between, silent, enormous, empty, is unlike anything we experience naturally on Earth. It also helps to imagine the distance in terms of a familiar object like a car, even though a car cannot drive through space. If a vehicle could travel continuously at highway speed without stopping, it would take months to reach the Moon. Meanwhile, light makes the trip in just over a second. This difference again shows how slow human movement is compared to cosmic distances. The Moon is close in astronomical terms, but unimaginably far in human terms. The contrast is both humbling and oddly comforting. It reminds us that our sense of scale is rooted in our own limitations, not in the nature of the universe. Another aspect of the Earth-Moon relationship that reveals scale is the size of Earth's shadow. During a lunar eclipse, when Earth passes between the Sun and the Moon, the shadow cast by the planet covers the Moon completely. That shadow stretches across space in a cone that tapers, but remains wide enough to engulf a world thousands of kilometers across. This demonstrates something easy to overlook. Earth, though small in the cosmic scheme, still carries weight and presence within its immediate surroundings. Its shadow reaches far enough to reveal the invisible relationships between celestial bodies. The Moon stays in orbit because Earth's gravity holds it close, even across great distance, and in turn, the Moon gently influences Earth's tides and rotation. The two bodies maintain a connection despite the gap between them. When we think about the Moon's distance, we often imagine it as an empty stretch of blackness, but in reality it represents a boundary between what humans have physically touched and what remains untouched. We have travelled beyond Earth only once to this nearby world. The space between them marks the limit of our steps so far, and because the distance is so large, the achievement feels monumental. The fact that humans once crossed that gap using limited technology from the mid-20th century adds even more awe to the scale. We built machines capable of pushing through hundreds of thousands of kilometres, landing on another world and returning safely. That accomplishment didn't shrink the distance. It simply showed that distance could be navigated with enough effort, patience, and careful design. Thinking about all this brings an interesting realization. The moon is not far or close in the way we normally think about distance. It sits in a category of its own, a liminal space between the familiar and the cosmic. Close enough to observe in detail, far enough to challenge imagination. Present in our sky, absent from our reach. It is part of our world, but also separate from it. That balance makes it a perfect reference point as we move outward to understand the solar system more fully. Once you've spent a little time thinking about the space between Earth and the Moon, it becomes easier to imagine the wider region that surrounds both of them. The moment we step outward into the solar system, the scale begins to stretch in ways that are difficult to picture at first. Nothing in human experience prepares us for how spread out everything becomes. The planets float in orbits that seem orderly when drawn on a diagram, but in reality the distances between them are so large that even calling them neighbours feels slightly inaccurate. And yet, for all that space, the solar system has a calmness to it. Nothing drifts chaotically in and out. The planets move in predictable paths. The sun glows steadily. Everything seems unhurried, as though the neighbourhood has settled into a long, quiet routine. The sun, sitting at the centre, appears enormous to us when we think about it on its own. But the solar system is much larger than the star at its heart. If the sun were reduced to the size of a large sphere you could hold in both hands, Earth would shrink to the size of a small bead orbiting many meters away. The moon would be a tiny speck circling that bead. And all the other planets would lie even farther out, with gaps so wide between them that you might hesitate before walking from one to the next, because the emptiness would feel like it goes on forever. This is the first thing people often misunderstand about the solar system. It is mostly distance. Space dominates far more than objects do. Those vast gaps create a sense of stillness that is hard to describe. When we think of a neighbourhood, we imagine houses situated close together. But in the solar system, every house is separated by huge stretches of nothing. If the planets were placed on a scale model along a long stretch of road, you could walk for minutes without seeing the next one. Even the inner planets, often described as the compact region near the Sun, sit far apart compared to any distance on Earth. And once you move outward toward the gas giants, the scale expands dramatically. Standing on Earth, looking up at the sky, it is natural to assume the solar system is filled with activity. The sun rises, the planets move, the moon cycles through phases, but almost all of this motion is slow. Extremely slow. The planets take years to complete a single orbit. Jupiter circles the Sun roughly every 12 Earth years. Saturn needs nearly 30. And if you wander mentally out to the edges, to Neptune or beyond, the orbits grow so long that it becomes difficult to attach a human sense of time to them. Neptune takes more than 160 Earth years to complete one trip around the Sun. That means no one has lived long enough to witness a full Neptune year. This slow rhythm contributes to the neighbourhood's peaceful atmosphere. While Earth spins rapidly and our lives move in quick cycles of days and nights, the solar system drifts almost lazily. If you were to imagine yourself floating above the Sun, watching the planets move, you wouldn't see them racing. They'd glide along their paths like boats on a lake with no wind. That kind of movement is soothing to picture because it reminds you that not everything in the universe operates on the same pace as human life. Out there, change is measured in decades, centuries, and millennia, not hours or minutes. The neighbourhood has its own structure. Closest to the Sun lie Mercury, Venus, Earth, and Mars, the inner planets. They are relatively small, made mostly of rock and metal. When placed on a diagram, they appear clustered together. But even here, the distances between them would feel enormous if you tried to cross them physically. Mercury, for example, is tens of millions of kilometres away from Venus. and similar distances separate Venus from Earth and Earth from Mars. If you tried to travel between these planets using any technology we have today, the journey would take months, sometimes longer, depending on their positions in their orbits. Beyond Mars, the solar system suddenly opens into an immense gap known as the asteroid belt. Many people picture the asteroid belt as a crowded region where rocks bump into one another constantly. But the reality is very different. If you were drifting through it, you would likely not see a single large rock nearby. The objects are so spread out that you could travel for days without encountering anything of note. This area reveals once again how empty the solar system really is. Even the parts we imagine as cluttered are mostly open space. Continuing outward, the gas giants appear next. Jupiter, the largest planet in the neighbourhood, dominates this region. If Earth were a small bead, Jupiter would be a sphere large enough to fill both your hands and then some. It contains more mass than all the other planets combined, and yet, despite its size, the distance between Jupiter and Saturn remains enormous. You could fit all the inner planets in the space between them and still have room left over. This pattern repeats again and again. Distance outnumbers substance. Saturn, with its rings, adds another layer to the scene. The rings look delicate, almost fragile when photographed, but they span a width greater than the distance between Earth and the Moon. Even then, the solar system's emptiness continues beyond them. Uranus and Neptune follow in orbit so far from the Sun that sunlight reaches them in a softened, faint way. It takes hours for the Sun's light to travel to Neptune. That detail alone hints at the vast size of the solar system. Light, which seems instantaneous on Earth, needs hours to cross the neighbourhood. Something else becomes clear when thinking about these distances. Earth, despite being the world we know best, occupies a very small zone in this larger arrangement. It's just one world on one orbit among many. From a quiet cosmic viewpoint, Earth doesn't appear as the busy, complicated place we experience daily. It becomes a single object drifting along a track, far from its neighbours, separated by hundreds of millions of kilometres. And yet the solar system feels coherent. Everything orbits the same star. Everything follows a set of stable paths. There is structure without crowding. The feeling of peacefulness in this neighbourhood comes not only from the slow movement, but from the predictability. The planets have followed their orbits for billions of years. Earth completes a lap every 365 days. Venus does so every 225. Jupiter takes its 12 years without rushing. Nothing in these motions suggests urgency. They simply continue, and as long as the sun shines, the pattern will remain. Comparing that to the pace of human life creates a contrast that is strangely grounding. While our schedules change rapidly, the solar system maintains a steady background rhythm. It's worth pausing to consider the sun itself. Everything in the neighbourhood orbits this star because of gravity. The sun contains more than 99% of the solar system's mass. Its pull shapes every planet's path. Without it, the neighbourhood wouldn't exist. And yet, the sun is not unusually large in cosmic terms. It's a medium-sized star. Not tiny, not immense, just ordinary. But because it is so close to us, it appears enormous from our perspective. This closeness makes us forget how much space lies beyond the sun's reach. If you imagine shrinking the solar system again into a scale model, with the sun as a sphere the size of a large lamp, Earth would be a tiny bead orbiting at a distance greater than most living rooms. Jupiter would be a much larger marble positioned down the hallway or across the yard. And Neptune would be so far away that you might need to walk for several minutes to place it correctly. The model reveals something surprisingly calming. Even with its immense size, the solar system has a kind of simplicity. A single star in the middle, a handful of planets spaced widely apart. A quiet arrangement that has remained unchanged for eons. Looking at it this way makes Earth feel both small and fortunate. Small because its size and orbit barely register in the overall scheme. Fortunate because it sits at just the right distance from the sun for liquid water to exist. This narrow band, often called the habitable zone, is not large. Move Earth slightly closer to the Sun and it becomes too hot. Move it slightly farther away and it becomes too cold. The solar system's wide reaches contain only this narrow ribbon where a world like Earth can thrive. That detail places the neighbourhood size in a new context. It may be enormous, but only a tiny region within it supports life as we know it. Thinking about these distances also reveals why human exploration has so far reached only the very edge of our neighbourhood. We have sent probes past the outer planets, but no human has yet travelled beyond the Moon. The distances involved create challenges we're not yet equipped to solve easily. Travelling from Earth to Mars takes months. Reaching Jupiter would take years. Moving farther out becomes even more difficult. The solar system is not unfriendly. It's simply too spread out for quick visits. This is part of its calmness. Space doesn't rush. It offers time in abundance, even if we can't make use of it in the ways we'd like. Another detail worth noting is how empty the solar system remains even when filled with space dust, asteroids, comets, and smaller objects. These elements exist, but they do not clutter the neighbourhood. A spacecraft travelling through the solar system has an extremely low chance of hitting anything unintentionally. The emptiness dominates. It creates an atmosphere of spaciousness that makes the neighbourhood feel quiet and unpressured. When you step back and picture the solar system in your mind, it becomes easier to understand why Earth feels so ordinary from a cosmic standpoint. Just one world, on one orbit, around one star. But that ordinariness has its own kind of comfort. Earth fits naturally into the neighbourhood. Its movements are steady. Its orbit doesn't shift unpredictably. It participates in the solar system's slow rhythm without needing to control anything beyond itself. There comes a point, as we keep moving outward from the familiar planets, when the Sun begins to change in our perception. Not physically, of course. It continues shining with the same steady output it always has. But the way we sense its presence begins to shift. We're so used to the Sun dominating our sky, warming our days, and defining every cycle of life on Earth, that it's easy to assume its influence extends in the same obvious way throughout the entire cosmos. Yet once we drift far enough away from the inner regions of the solar system, the Sun's identity starts to soften. It stops feeling like the central anchor of everything, and begins to resemble what it truly is in a broader context, one star among countless others. Understanding this transition requires stepping beyond the orbits we usually picture. The planets provide structure close to the Sun, and thinking about their paths helps us feel the solar system as a whole. But the solar system does not end where the planets end. It stretches far beyond them in regions that rarely appear on diagrams because they're simply too large to show. Even the outermost orbit of Neptune is only a small step into the Sun's full domain. To understand where the Sun stops being close, we need to explore much farther out, into distances that dwarf even the journeys between planets. Light is a good starting point. Near Earth, sunlight is strong enough to warm skin, brighten landscapes, and power nearly every biological process we know. At Venus, sunlight is stronger still. At Mars, it begins to weaken but remains recognizable. Beyond Jupiter, sunlight fades into something more gentle. By the time it reaches Saturn, it feels pale, faint compared to what we know. And when you drift outward to Uranus or Neptune, sunlight becomes something you might almost call thin. It still illuminates, but it no longer resembles the warm, bright presence we associate with daytime on Earth. It becomes more like a distant glow, something that feels detached from everyday experience. But even at Neptune's orbit, the Sun is still undeniably dominant. It remains the central gravitational force holding the planets in place. Spacecraft that venture through this region report sunlight that, while dimmer, still shapes shadows and highlights surfaces. It takes more than a pale glow for the Sun to lose its identity as the nearby star we think we know. To find the region where the Sun begins to step back into the background of the universe, we need to follow its influence to the boundaries where its light and particles finally cease to create a distinct zone. This involves understanding something called the heliosphere. The heliosphere is a vast bubble surrounding the solar system, formed by the solar wind, a stream of charged particles blowing outward from the sun in all directions. This bubble extends much farther than the planets, forming a kind of invisible cocoon around the entire system. Inside it, the sun's influence dominates. Outside it, interstellar space begins, where the environment is shaped not by the sun, but by the galaxy itself. Reaching the edge of the heliosphere requires travelling distances far greater than the ones we use to measure planetary orbits. Neptune orbits the Sun at about 30 astronomical units, meaning 30 times the distance between Earth and the Sun. But the boundary of the heliosphere lies around 100 astronomical units from the Sun, more than 3 times farther. Even at that distance, the Sun still shapes the environment, still pushes outward, still affects the particles moving through space. But beyond that boundary, something shifts. The Sun's wind slows, the pressure drops. Interstellar particles begin to dominate. The environment becomes part of the galaxy, not the solar system. This is where the Sun starts losing the feeling of closeness. The transition is subtle at first. There's no sudden wall or dramatic change. But gradually, the sense of being inside the Sun's immediate neighbourhood fades. The Sun becomes just another point of light behind you, and the environment begins reflecting the broader cosmos instead of the specific conditions created by one star. Only 2 human-made spacecraft have ever reached this region. Voyager 1 and Voyager 2 launched in the late 1970s and spent decades moving outward. They travelled past Jupiter and Saturn, one of them even visiting Uranus and Neptune. Eventually, after nearly 40 years of continuous journey, they crossed the boundary of the heliosphere. When they did, the measurements they recorded revealed the transition clearly. The density of particles changed. Magnetic fields behaved differently. The Sun's influence weakened enough that they were no longer inside its protective bubble. What's interesting is that even then, the Sun still appeared bright from their perspective. Not bright like Earth's daylight, but brighter than any star around it. However, the environment they entered was no longer shaped by the solar wind. It was shaped by the galaxy. In that sense, this is where the Sun stops being close. It becomes more of a distant anchor, something that shines but no longer dictates the conditions of space nearby. This shift marks the beginning of viewing the Sun the way the rest of the universe sees it, one of billions of stars scattered across the Milky Way. Understanding this change in perception helps us rethink the solar system's actual size. Many diagrams show the planets close together, often compressed just to make them fit on a page. In reality, the solar system is so large that most of it consists of empty space, influenced by the Sun's wind and gravity. And beyond the heliosphere lies a region even more sparsely populated. The galaxy does not immediately fill the space outside the solar bubble with new phenomena. Instead, you enter a quiet expanse of interstellar material that continues for light years before reaching another star. This brings us to a crucial realization. The closest star to the Sun, Proxima Centauri, sits more than 4 light-years away. That distance is so large that even light, which feels instantaneous to us, takes more than 4 years to cross it. The Voyagers, travelling at remarkable speeds compared to any everyday object, would take tens of thousands of years to reach the nearest star. That separation tells us something fundamental about our place in the universe. Stars that look close together in the night sky are separated by enormous silent gaps. The Sun only feels close because we live within its tight gravitational and luminous embrace. When we stand on Earth and look at the Sun, its size overwhelms our vision. It appears as a disk too bright to stare at, dominating the sky and setting the rhythm of day and night. But if you imagine drifting farther out, past the planets, past the boundary where the solar wind stops pushing outward, the Sun begins to shrink. At a large enough distance, it becomes a brilliant star, brighter than the others but no longer a blazing orb. When you reach the scale of the nearest stars, the Sun looks like a point of light, It still shines strongly compared to its neighbours, but nothing about it suggests the familiar warmth and brightness it gives to Earth. That transformation is important because it shows how relative our perception is. The Sun feels immense because we are so close to it. But most stars in the galaxy are similar to the Sun. Some are larger, some smaller, some hotter, some cooler. The Sun's ordinary nature becomes clear once you drift far enough away. Its uniqueness fades, not because it loses any of its intrinsic properties, but because its context changes. Surrounded by billions of stars, it becomes one among many. This shift also helps ground the idea of cosmic scale. When the Sun stops dominating the environment, the universe reveals one of its central characteristics: decentralization. There is no single focal point, no center that everything orbits. Instead, there are countless stars, each with its own region of influence, its own planetary systems, its own bubble of space shaped by its wind and gravity. The galaxy is a collection of neighborhoods, each with its own quiet boundaries. And the Sun's neighborhood is just one of them. Even after leaving the heliosphere, the Sun's light remains detectable over vast distances. It weakens steadily, but it never stops completely. Light spreads indefinitely through space, growing fainter the farther it travels. But there is a point where starlight becomes so faint that it blends with the background glow of the galaxy. This blending is where the Sun truly becomes just another star. Not because it changes, but because the scale we are considering has grown so large that any individual star becomes only a small piece of a much larger pattern. This perspective does something subtle to our view of Earth. When the Sun becomes just a star among many, Earth becomes something even smaller, a tiny world orbiting an ordinary star in a galaxy filled with other worlds, many of which we may never detect. Yet that smallness does not diminish Earth's meaning. It simply places it in a realistic setting. Our world is unique to us because it is the only place where we experience life, consciousness, connection, and time. But in the cosmic expanse, it becomes a point in a pattern, one of many potential homes scattered through the universe. The idea that the Sun can stop feeling close might seem unsettling at first, but the more you think about it, the more reassuring it becomes. If the Sun were the centre of the universe, our place within it would feel more rigid. Instead, we live in a universe without a single centre, where all places can be viewed as equally valid points of reference. This openness creates room for perspective, allowing us to understand our position without needing the universe to revolve around it. Continuing outward from the region where the Sun's influence fades will eventually carry us into spaces dominated not by the solar wind, but by the structure of the Milky Way itself. The galaxy becomes the next frame of reference, a wider neighbourhood that defines the movement of stars, gas and dust. Once we reach that scale, the Sun's identity shifts fully. Its light still shines, its gravity still shapes its own tiny region. But compared to the structure of the galaxy, it becomes a small participant in a much larger arrangement. In this way, moving outward helps us gradually adjust our expectations. Earth is small compared to the Moon's distance. The solar system is wide and quiet, with planets separated by vast stretches of space. If you imagine drifting far enough from the Sun to see it as just another point of light, the next natural step is to look around and notice the environment that surrounds it. Not the planets or the outer reaches of the solar system, but the much larger structure that holds everything together. The Milky Way is where the Sun lives, and once you begin to picture it, the scale expands so dramatically that everything we've talked about so far starts to feel compact. The solar system becomes a small bubble. The distances between planets become narrow corridors. Even the boundary where the Sun stops shaping the environment becomes a tiny region tucked inside a much wider expanse. The Milky Way is not just large, it is enormous in a way that redefines what distance means. Unlike the solar system, which has a clear centre and well-defined orbits, The Milky Way is more like a vast collection of stars arranged in a broad, flattened shape with a central bulge and winding arms. The Sun sits roughly halfway between the centre and the outer edge, moving through the galaxy at a steady pace. Even though the Sun's motion is fast by everyday standards, it takes more than 200 million years to complete a single orbit around the Milky Way. That alone gives you an idea of the galaxy's size. If an entire human civilization rose, flourished, and disappeared, the Sun would barely move along its galactic path. Trying to picture this requires adjusting our sense of scale again. The galaxy contains hundreds of billions of stars. Many of them are similar to the Sun. Others are larger, smaller, hotter, cooler, older, or younger. Some are grouped in clusters. Others drift more quietly along the spiral arms. The stars are spread out so far apart that each one occupies its own enormous region of space. The gap between any two typical stars is measured in light years, meaning light travelling at its incredible speed still needs years to cross from one to another. If we were to shrink the entire solar system down until the Sun was a tiny grain of sand, the nearest star would be another grain sitting kilometres away. This spacing creates a feeling that is different from the solar system's wide neighbourhoods. The solar system feels spacious, but the Milky Way feels almost endlessly open. There is no sense of closeness between stars. Even the dense-looking bands of light we see in the night sky are made of countless stars so distant that their light blends together. When we talk about strolling through the galaxy, we don't mean moving from one star to the next as if they were trees in a forest. We mean drifting through a region where the distances are so vast that individual stars become markers in an immense slow-motion landscape. Looking at the Milky Way from Earth gives only a partial sense of its structure. On clear nights, especially in places without artificial light, the galaxy appears as a faint band stretching across the sky. That band contains stars, gas, dust, and distant clusters that lie along the plane of the galaxy. We see it from inside, which means our perspective is limited. It's like standing in a wide field surrounded by tall grass and trying to understand the entire landscape based only on what's around you. But the faint glow is enough to hint at the scale, the structure, and the vast distribution of stars. If you were to leave the solar system and continue drifting outward, the Sun would eventually take its place among the stars that make up this glowing band. From a great enough distance, you wouldn't be able to pick it out easily. It wouldn't shine brighter than every other star. It would simply join the pattern, another point of light among billions. That realization brings an interesting shift in perspective. The Sun, once overwhelming in the sky of Earth, becomes small and unremarkable when compared to the galaxy as a whole. One of the most notable features of the Milky Way is its spiral structure. These spirals aren't tightly wound like springs. They're more like gentle curves that stretch across tens of thousands of light years. The Sun sits in one of these arms, not near the edge, but not close to the centre either. This position is sometimes described as quiet, not because anything like sound exists in space, but because the region around us is relatively calm. Near the galactic centre, stars crowd closer together. Gravity becomes stronger. Conditions grow more energetic. Out here, far from that region, the environment is steadier, with stars spaced widely apart. As we drift mentally through the Milky Way, it becomes useful to imagine the galaxy as a vast, soft swirl of stars that don't cluster tightly, but spread in patterns that take ages to change. Nothing in this environment feels hurried. While stars orbit the centre, they do so at speeds that look impressive in numbers, but feel slow in practice because the distances are so immense. Even the fastest moving objects take thousands of years to make progress you could notice from afar. This slow pace gives the galaxy a sense of quiet motion, a long-term drift rather than a rapid rotation. It's easy to assume that a place with so many stars would feel busy, but the Milky Way is mostly empty. If you placed yourself between two stars, you could travel for years without encountering anything else. Dust and gas fill the space between stars. but they are spread out so thinly that you would never feel them. The emptiness creates a sense of spaciousness that makes the galaxy feel open despite containing so many stellar systems. Another interesting detail is the variety of stars that populate the Milky Way. Red dwarfs, which are smaller and cooler than the Sun, make up most of the population. They burn slowly and can live for trillions of years. Larger stars burn brighter but use their fuel quickly and often end in dramatic explosions. Some stars form binary systems, orbiting one another in a slow, predictable dance. Others group into clusters, forming dense pockets of stars that share a common origin. These differences give the galaxy texture. Instead of looking uniform, the Milky Way becomes a mixture of environments, each with its own character. When thinking about the galaxy, it helps to picture these stars not as glowing dots, but as systems with their own planets, moons, and potentially environments we have never imagined. The Milky Way contains more stars than we could count in several lifetimes, and many of these stars likely host planets. Observations from telescopes suggest that planets are common. Some orbit close to their stars, others far away. Some are rocky, some gaseous, and some icy. Many systems differ greatly from our own. This variety adds another layer to the galaxy's scale. We're not looking at isolated stars. We are looking at billions of potential worlds. When we place Earth in this context, its size, distance, and significance shift again. Earth is no longer just a small world orbiting a single sun. It becomes one of countless small worlds, orbiting one of countless suns. The galaxy holds so many potential homes that Earth becomes part of a pattern rather than an exception. That doesn't make Earth less meaningful. It simply shows that the universe has room for diversity far beyond what we see in our immediate surroundings. Something else worth noting is how long it takes for light to travel across the Milky Way. The galaxy is around 100,000 light-years wide. That means even light, moving at the fastest speed possible, needs tens of thousands of years to cross from one side to the other. If a civilization existed at the opposite edge and pointed a telescope toward Earth, the light reaching them today would show Earth as it was before humans existed. Communication across such distances becomes impossible with anything like the methods we know. The galaxy's size stretches not just space but time. Despite this enormity, the Milky Way remains orderly. Stars follow predictable orbits. Spiral arms drift slowly. Clusters move through the galaxy in long, sweeping paths. Clouds of gas collapse to form new stars. Older stars fade, cool, or explode. Everything changes, but on scales too large and slow for us to feel directly. From our perspective, the galaxy remains stable, a long-term environment that shapes the conditions for countless systems. Another aspect of the Milky Way is the central bulge. This region contains older stars and a dense arrangement of matter. At its core sits a supermassive black hole, millions of times more massive than the Sun. It doesn't act like a vacuum cleaner, pulling everything in, but instead shapes the orbits of stars around it. Even so, life near the centre would experience a very different environment compared to our quiet region. The increased density of stars, higher radiation levels, and energetic events create a more active landscape. Out here, far from the centre, conditions are calmer, more steady, better suited for long-term stability. When thinking about strolling through the galaxy, imagine drifting across regions where stars appear in clusters at times and fade into sparse areas at others. The density shifts, but the overall arrangement feels continuous. Moving from one region to another might take thousands of years, but in the imagined scale of our thoughts, it becomes a slow, steady journey without abrupt boundaries. The sun's motion through the Milky Way is equally gradual. As it travels, it passes through different regions of varying density. Sometimes it wanders through areas rich in gas, sometimes through quieter stretches. These changes influence the solar system subtly, affecting comet paths or dust patterns, but rarely causing dramatic disruptions. This slow movement emphasizes again how the galaxy's scale shapes everything within it. If you picture the galaxy as a kind of broad, starry landscape, the sun becomes a traveller moving through it on a journey that will never end. And Earth, orbiting the sun, travels with it, drifting through regions so large and so slow-moving that human history becomes a momentary flicker. Civilizations rise and fall while the sun barely shifts in its galactic orbit. Placing ourselves inside this larger structure helps us understand how small the solar system truly is. The entire region where the planets orbit becomes a tiny bubble in a vast sea of stars. The heliosphere becomes a faint outline barely noticeable compared to the galaxy's width, and the distance between the sun and the nearest stars becomes the smallest unit in a chain of distances that stretches across the Milky Way. This perspective doesn't diminish the solar system. Instead, it gives it context. The sun's neighbourhood becomes one patch of a much larger arrangement. Earth's orbit becomes one of billions of potential orbits, and the galaxy becomes not a distant concept, but the environment we inhabit without noticing. Reaching a point where the Milky Way's size feels even partially familiar makes it easier to start noticing the patterns within it. Once you're far enough away from the solar system to view the galaxy not as scattered points, but as a connected structure, certain shapes come into focus. Stars don't float randomly. They gather in long arcs, dense clusters, and broad regions where the light blends together. These arrangements aren't decorative. They're the result of gravity shaping matter over billions of years. And as we move through this scale in our imagination, it becomes clear that the galaxy is made of patterns that look less like chaos and more like a slow, natural flow of stars across enormous distances. One of the first features you might notice is how stars collect into thick bands, forming what look like clouds from afar. These clouds aren't made of vapour. They're made of stars so numerous that the light from each one blends with the others. When seen from Earth, these clouds appear as bright zones within the Milky Way's faint band. But if you picture yourself drifting through the galaxy, the impression changes. Instead of a flat streak across the sky, the star clouds reveal themselves as dense regions woven through the spiral arms. These clouds are not uniformly bright. Some areas glow intensely because they contain thousands of stars gathered in a relatively small region. Others are dimmer, where starlight must travel through gas and dust before reaching you. The dust doesn't simply hide stars, it shapes the distribution of light, making some regions appear softer and others more sharply defined. Over long spans of time, gas within these clouds collapses under gravity, forming new stars, while older stars drift outward through the arms. The clouds are not static. They are part of a slow cycle of creation and movement that sustains the galaxy's structure. The idea of rivers of light becomes more apparent when following the spiral arms. These arms aren't solid objects, nor are they pathways that stars follow in a strict sense. They're regions where stars, gas and dust are more concentrated. If you imagine tracing one of the arms, you'd be following a path defined not by a material surface but by a density pattern. The stars in the arms move independently, each on its own orbit, but the collective motion creates the impression of a flowing structure, much like leaves drifting together on a slow-moving current. This pattern can be difficult to imagine because we tend to think of structure as something fixed, but the spiral arms shift slowly over time. They maintain their overall shape, yet the stars inside them are constantly replaced as they move. New stars form in the arms because the gas density is higher there. Older stars drift outward or inward as their orbits evolve. In this sense, the arms are more like traffic jams than permanent objects. Cars move in and out, but the congestion remains because of the dynamics of the road. The arms remain visible even as their contents change. Thinking of the Milky Way as a place shaped by these large-scale patterns helps reframe how we see our own position in the galaxy. The sun sits in a quiet region of one spiral arm, specifically a small segment often called the Orion Arm or Orion Spur. It's not located in one of the major arms, it lies between them, occupying a space that feels ordinary compared to the galaxy's more crowded zones. This location is neither too dense nor too empty. It offers stability over long periods, giving Earth the environmental consistency needed for life to develop. When we talk about our place in the spiral, we're describing more than just a set of coordinates. We're acknowledging the conditions that made Earth's history possible. If the Sun were closer to the galactic centre, the increased density of stars and higher radiation levels might have created a more unpredictable environment. If the Sun were too far outward, the scarcity of heavy elements formed in earlier generations of stars could have limited the building blocks available for planets like Earth. The position in this modest spiral segment provided a balance. Enough material to form worlds, enough stability to allow them to persist. Inside these clouded regions and streams of starlight, a quiet complexity unfolds. Stars form in clusters, often beginning life close to one another. Over millions of years, the clusters spread out as stars move along their individual paths. Some clusters remain intact for long periods, held together by gravity. Others slowly disperse. This constant motion contributes to the rivers of light we see from afar. Individual stars don't shape the pattern, but collectively they create a flowing distribution that defines the arm's appearance. Gas and dust in the spiral arms also play a significant role in shaping the environment. These materials scatter starlight, making some regions appear darker or more muted, but they also provide the raw material for future stars. Over time, dense regions collapse to form stellar nurseries, areas where hundreds or thousands of new stars are born. Many of these stars will eventually drift away from these nurseries, spreading across the arm and further blending into the long luminous patterns that extend through the galaxy. A surprising aspect of this structure is how much space exists between stars. Even in the densest parts of the arms, stars remain far apart. You could travel vast distances without coming close to another stellar system. The brightness of the arms comes not from proximity, but from population. Thousands of distant stars contribute tiny amounts of light that merge into a soft glow. From afar, these contributions accumulate into bright, elongated patterns. As we picture moving through these regions, the sense of motion doesn't feel like navigating a crowded environment. It feels more like drifting through a wide landscape dotted with points of light. The density changes gradually. Clusters appear and fade. Bright regions come into view and then pass as you continue along. There is no sense of rushing or of obstacles. Everything unfolds at a pace dictated by gravity and time, not by urgency. Understanding these structures also helps clarify why Earth's sky looks the way it does. The bright band of the Milky Way exists because we are viewing the galaxy edge on from within one of its arms. We are looking through layers of stars, gas, and dust that align along the plane of the galaxy. This view compresses the distribution into a narrow band. If we lived near the galactic centre, the sky would be filled with many more stars, and the band would appear wider and brighter. If we lived far from the plane of the galaxy, the band would appear fainter or might not be visible at all. Our specific position shapes our perception of the galaxy's structure. Another feature that becomes noticeable when thinking about the Milky Way's patterns is the presence of dark lanes cutting through the bright regions. These aren't voids, they're areas filled with thick dust clouds that block starlight. When seen from Earth, they create the impression of gaps or divisions in the glowing band. But if you drifted through those regions, the darkness would dissolve into scattered points of light, just as bright as anywhere else once you move beyond the dust. These lanes highlight how gas and dust shape the appearance of the galaxy without fundamentally changing its structure. Beyond the spiral arms, the Milky Way contains a central bulge filled with older stars. This region is more spherical and dense compared to the flat plane of the spiral. The stars here belong to earlier generations, often formed before the spiral arms took shape. Their distribution creates a soft, bright core when the galaxy is viewed from outside. But from our location, the bulge appears as a brighter region near the constellation Sagittarius. The galaxy's centre is not visible directly due to dust, but the glow from the bulge hints at the dense stellar population within it. Thinking about our place within these patterns encourages a different understanding of Earth's position. We are not near the centre, nor at the edge. We occupy an intermediate region that offers a stable vantage point. The spiral arms sweep around us in long arcs. Star clouds drift across the galactic plane. The rivers of light flow along paths shaped by gravity, and Earth, orbiting the Sun, moves through this environment without needing to influence more than its own small system. Another way to understand the galaxy's scale is to think about how long it takes for changes to become noticeable. A spiral arm doesn't shift visibly in a human lifespan. Even over centuries, the pattern remains the same. But over millions of years, stars drift in and out. The gas clouds evolve. New stars form and older ones move along their paths. The galaxy is dynamic, but the changes happen slowly enough that they create a sense of long-term steadiness. This slow evolution contrasts sharply with the rapid pace of life on Earth. While seasons change, civilizations develop, and technology advances within short periods, the Milky Way moves at a different tempo. The patterns we see in the sky today resemble the patterns seen by ancient observers thousands of years ago. The rivers of light have not shifted significantly. The clouds of stars remain in roughly the same positions. That stability provides a quiet backdrop to human history. No matter how quickly life moves, the galaxy drifts at its own deliberate pace. Thinking about our place in the spiral also introduces the idea that our location affects what we can observe. Telescopes reveal structures in the galaxy, but our position inside the disk limits our view. We cannot see the galaxy's exact shape directly. Instead, we deduce it from patterns of light, star distributions, and the motion of objects. Our understanding improves over time, but it remains incomplete in a way that feels surprisingly gentle. The galaxy doesn't reveal everything at once. It offers glimpses, patterns, and suggestions, leaving room for continued exploration. If we imagine ourselves continuing this journey through the galaxy, we find that the patterns extend much farther than we might expect. The spiral arms sweep outward for tens of thousands of light years. The density of stars shifts gradually. The distribution of gas and dust changes with position. But the overall structure remains coherent. There is no abrupt edge. Instead, the spiral arms taper off into regions where stars become sparser, eventually blending into the outskirts of the galaxy. As we drift mentally across these starry dunes, the solar system becomes a distant memory. Earth's orbit fades into insignificance. The Sun becomes another point of light, and the patterns of the Milky Way become the primary frame of reference. When the Milky Way becomes familiar enough to imagine from a distance, something in the mind naturally wonders what lies beyond it. Once you understand that our galaxy is just one structure among many, the next step is to lift your attention toward the wider sky, the one that contains not only stars but entire galaxies scattered across space. The shift from thinking about individual stars to thinking about whole galaxies marks another major expansion in scale. It stretches what we mean by distance and reshapes what we consider numerous. The Milky Way's hundreds of billions of stars sound overwhelming until you compare them to the number of galaxies beyond it. That comparison can create a kind of quiet surprise, not a dramatic shock, but a soft awareness that the universe is far more populated than anything we see from Earth's surface. Looking up at the night sky, most people see only stars from our own galaxy. Even with good eyesight and clear conditions, nearly every point of light belongs to the Milky Way. Yet sprinkled among them are faint objects that don't behave like stars. They appear as tiny, hazy patches, too big to be stars, too small to show structure with the naked eye. These are distant galaxies. Even though they look dim, each one contains millions or billions of stars of its own. Their presence in the night sky is subtle, easy to overlook if you're not searching for them, but they hint at the vast environment that lies beyond the Milky Way's boundaries. To understand what it means to have a sky filled with galaxies, imagine placing the Milky Way on a map where each galaxy appears as a single point. That point would not be isolated. It would sit among countless others, forming clusters, groups, and larger arrangements that stretch across space. The nearest large galaxy, Andromeda, is similar in size to the Milky Way and sits about 2.5 million light-years away. A distance like that is almost impossible to visualize. Even light, covering 300,000 kilometers every second, needs millions of years to bridge that gap. Yet Andromeda is close compared to many other galaxies. It's part of our local group, a small collection of galaxies that includes the Milky Way, Andromeda, the Triangulum Galaxy, and dozens of smaller satellite galaxies. If you picture the Milky Way as a glowing swirl in space, Andromeda would be another swirl drifting nearby, both moving slowly toward each other. Over billions of years, the two galaxies will eventually merge, but this isn't something that resembles two objects colliding violently. Instead, it's more like two clouds drifting into one another, their stars passing through enormous amounts of space without touching. The gravitational effects will reshape the galaxies, but the vast distances between stars mean that individual collisions are unlikely. This gentle nature of galactic interaction contrasts with the dramatic idea of galaxies crashing. Space remains mostly open even in these large-scale processes. What makes the idea of a sky full of galaxies so striking is not just how many there are, but how far away they sit. Each one is separated by millions of light-years. This spacing means that galaxies hardly affect each other's day-to-day dynamics. Instead, they drift through the larger structure of the universe as part of a quiet, long-term arrangement. Their motions unfold over billions of years, with changes happening so slowly that the universe seems almost still when viewed from our human perspective. Beyond the local group lies a much larger structure called the Virgo cluster. It contains thousands of galaxies. Some of these galaxies are spirals like the Milky Way. Others are giant ellipticals, shaped more like smooth ovals made up of older stars. Many are smaller, irregular galaxies with chaotic shapes. If you could view the Virgo cluster from afar, it would look like a glowing cloud of tiny lights, each representing a galaxy. Yet the cluster would not feel dense. The galaxies are still separated by vast distances. They gather as a group, but they do not crowd one another in any familiar sense. Thinking about the Virgo cluster offers another way to understand the universe's population. If we could somehow stand outside the cluster and observe it, we would see an arrangement of galaxies that forms patterns similar to the star clouds and rivers of light inside the Milky Way, only on a scale far larger. Bright cores, faint outskirts, bridges of galaxies and long arcs of structure appear when viewed from a distant vantage point. The cluster becomes a kind of city in space, filled with inhabitants, each of which is a galaxy with its own internal population of stars and worlds. This is where the idea of countless worlds begins to take on a different meaning. When we think of stars, we might imagine that many of them could have planets. But when we think of galaxies, that possibility multiplies dramatically. Every galaxy contains billions of stars. If even a small fraction of those stars have planets, the number of worlds becomes staggering. Worlds bathed in different kinds of light, worlds orbiting different kinds of stars, worlds with environments unlike anything we know. The details vary, but the scale remains consistent. The universe doesn't just hold a handful of planets, it holds more than we can imagine. The soft shock of this realization doesn't come from fear or confusion. It comes from a gentle widening of perspective. Once you understand that Earth is one world among many in the Milky Way, and that the Milky Way is one galaxy among many in the observable universe, the meaning of countless becomes clearer. Not because we can count them, but because the numbers exceed anything we normally handle. This isn't a chaotic abundance. It's a quiet one. These worlds don't crowd together. They fill a universe where space itself is the dominant feature. Most galaxies lie so far away from us that their light has travelled for millions or billions of years before reaching Earth. When we observe them, we see them as they were long ago. A galaxy whose light reaches us now may no longer exist in its current form. It might have merged with another galaxy, formed new stars, or changed shape. Our view is always delayed because distance stretches time in ways we don't experience on Earth. This delay doesn't distort the beauty of the galaxies. It simply reminds us that looking at space means looking into the past. Another layer of understanding appears when we consider galaxy clusters not as isolated collections, but as part of an even larger structure. Clusters group together into superclusters. These superclusters form enormous filaments and walls that span hundreds of millions of light years. Between them lie vast voids, regions with very few galaxies. These patterns create a cosmic web, a large-scale structure that gives the universe its shape. The Milky Way sits in one small part of this web, connected to other structures through gravitational relationships so gentle and slow that billions of years pass before the shapes shift noticeably. In this context, the sky filled with galaxies becomes a map of the universe's architecture. Each dot on this map corresponds to an immense system of stars and worlds. The beauty of this arrangement is not in its complexity, but in its scale. The universe formed these structures naturally through the slow action of gravity on matter spread throughout space. Galaxies drift toward clusters. Clusters drift towards superclusters. The cosmic web forms through these interactions, not because of any external design, but because matter follows the rules of gravity and time. This perspective also reshapes how we think about our own galaxy. The Milky Way is not unusually large or small. It is a typical spiral galaxy. It occupies a position in its local group that offers stability. It belongs to a larger cluster that contains thousands of other galaxies, and it sits in a cosmic web filled with structures far beyond its boundaries. The Sun's presence in this arrangement is modest. Earth's presence is smaller still. Yet none of this diminishes the uniqueness of our experience. Our world is the frame through which we observe everything else. The universe doesn't need to revolve around Earth to feel meaningful. Something subtle happens when we imagine moving through these vast structures. The distances become so large that the mind begins to treat them differently. Instead of trying to picture kilometers or light years, we shift into a mode where space becomes an open environment, not something we measure in familiar terms. Galaxies become landmarks. Clusters become regions. The cosmic web becomes a backdrop. This shift brings a sense of calm because it removes the pressure to comprehend the exact distances. Instead, we understand the relationships and the scale without needing to dwell on precise numbers. This idea becomes even clearer when considering how empty space remains despite the abundance of galaxies. Even in the densest clusters, galaxies remain separated by millions of light years. The vastness of space doesn't diminish its content, it simply spreads it out. The sky may contain countless worlds, but they are not crowded. They exist peacefully in an environment shaped by gravity and time. Thinking of galaxies this way gives the night sky a different feel. When you look up and see stars, you're seeing only a fraction of what exists. Most of the universe's galaxies lie beyond direct human sight. Telescopes reveal them, but our eyes cannot. Yet their presence shapes the cosmic structure around us. They form the long arcs, the clusters, and the filaments that make up the universe's large-scale arrangement. And Earth, orbiting the Sun, sits quietly within this vast system. As soon as galaxies become familiar enough to imagine a single point scattered across space, the next layer of structure starts to reveal itself. Galaxies rarely drift entirely alone. They gather into groups and clusters because gravity pulls them toward one another over billions of years. And once you see that clusters form, it becomes clear that they also tend to connect to even larger structures. This is the scale where the universe stops behaving like a collection of separate islands and starts resembling something more like a network. The objects are enormous, the spaces between them even more so, yet everything belongs to a larger pattern shaped by forces acting over unimaginable spans of time. Thinking about these clusters begins by revisiting the galaxies we've already pictured. The Milky Way belongs to a small group called the Local Group, which contains around 50 galaxies of varying sizes. Some are large spirals like the Milky Way and Andromeda. Others are much smaller dwarfs orbiting the larger ones. The local group is a modest neighbourhood by cosmic standards, but even this small structure already spans millions of light years. The galaxies in it are bound together by gravity. They drift, shift positions, and slowly move relative to one another, but they remain part of the same gravitational family. Groups like ours are not unusual. They're common throughout the observable universe. Wherever you look, galaxies gather in ways that suggest they're not content to float entirely alone. But these groups can also be part of something even larger: clusters. A cluster contains hundreds or thousands of galaxies, all orbiting around a common centre of mass, much like stars orbit the centre of the Milky Way. These clusters are some of the most massive structures held together by gravity. Their combined mass shapes the movement of galaxies inside them, forming an environment where everything responds to the pull of the cluster as a whole. The Virgo cluster is a good example of this. It sits around 50 million light-years away and contains thousands of galaxies. Some are enormous ellipticals, smoother and older than spirals like the Milky Way. Others are irregular or smaller systems shaped by past interactions. The cluster is not tightly packed in the way one might imagine. Even here, galaxies remain separated by vast distances, but the cluster's overall gravitational pull keeps them from drifting apart indefinitely. One of the surprising features of these clusters is that most of their mass doesn't come from the galaxies themselves. It comes from something called dark matter, a form of matter that does not emit or absorb light, but exerts gravitational influence. Dark matter acts as the invisible scaffolding of the cluster, holding the galaxies in place. Without it, the galaxies would not move the way they do. The cluster would not remain bound. The presence of dark matter adds another layer to the structure we're imagining. It suggests that even the patterns we see are supported by components we can't visually detect. Clusters contain not only galaxies, but also extremely hot gas that fills the space between them. This gas is so thin that you wouldn't feel it, but it's heated to millions of degrees and emits X-rays detectable by telescopes. Its presence tells us the cluster's environment is active, even if it seems tranquil from afar. Yet even within this environment, the distances remain vast, and the overall impression remains one of slow, quiet motion. From clusters, the scale expands again into superclusters. These structures contain multiple clusters, groups, and many individual galaxies spread out across tens or hundreds of millions of light-years. The Virgo cluster, for example, is part of the Virgo supercluster, which also includes the local group and many other systems. Even though the name suggests a single unified structure, a supercluster is not held together as tightly as a cluster. Its components are loosely connected, linked by gravity, in a way that creates a broad region of increased density compared to the surrounding voids. The more we examine these structures, the more the universe begins to resemble a web. The clusters and groups occupy nodes within this web, connected by filaments of galaxies that stretch across large distances. Between these filaments lie vast regions known as voids, where very few galaxies exist. These voids are not empty, but their density is extremely low compared to the filaments. The pattern resembles something organic, not because it was designed that way, but because gravity naturally shapes matter into these structures over billions of years. Understanding the cosmic web requires stepping even farther back in scale. If you could zoom out until individual galaxies shrink into tiny dots and clusters become faint smudges, the web would reveal itself as an interconnected arrangement of threads and nodes. Some filaments stretch hundreds of millions of light years. Some clusters anchor the intersections. Some voids span such great distances that a single galaxy within them would feel incredibly isolated. This distribution formed as matter clumped under gravity shortly after the universe began expanding. Regions denser than average grew denser over time, pulling in more matter and forming the nodes and filaments. Regions less dense expanded into the voids. The cosmic web is not static. It evolves slowly as galaxies merge, clusters grow, and matter continues to move. But the overall shape remains consistent over billions of years. This long-term stability contrasts with the short-term changes we experience on Earth. The continent shifts, climate changes, and species evolve all happen quickly compared to the pace of cosmic evolution. In the cosmic web, change is measured on a scale so large that even human history is too brief to register as more than a moment. Thinking about this structure gives us a new perspective on our place in the universe. The Milky Way occupies a position within the Laniakea supercluster, an enormous region containing tens of thousands of galaxies. Laniakea itself spans more than 500 million light-years. This region is defined not by sharp boundaries, but by the flow of galaxies toward a common gravitational centre. The name Laniakea means immense heaven, an appropriate description for a structure so large that light takes 500 million years to travel across it. Within this supercluster, the Milky Way feels incredibly small, not in a diminishing sense, but in a way that shifts our sense of proportions. Our galaxy is one among many. Our cluster is one node among countless nodes. Our position is part of a much larger and graceful arrangement. The universe does not crowd its structures together. It spreads them out across vast distances, giving each region room to exist within the larger web. Another aspect of the cosmic web worth understanding is the role of expansion. The universe as a whole continues to expand, and this expansion stretches the distances between superclusters. Inside clusters, gravity is strong enough to hold galaxies together. Inside superclusters, gravity loosely organizes clusters, but on scales larger than superclusters, gravity is not strong enough to overcome the expansion. As a result, superclusters drift apart from each other over time. The cosmic web becomes more stretched as the universe ages, yet the internal structure remains intact on smaller scales. This expansion also affects how we see distant galaxies. Their light is stretched, becoming redder due to the expansion of space. This redshift allows astronomers to measure distances and map the distribution of galaxies across the universe. The patterns revealed through these measurements confirm the presence of the cosmic web. The filaments, voids, and clusters emerge clearly when viewed on large scales. As we imagine drifting through this structure, the sense of size becomes almost beyond comparison. Moving from one galaxy to another requires imagining millions of light years. Moving from one cluster to another multiplies that scale. Travelling across a supercluster requires even larger distances. Yet the transitions feel gradual because the universe changes smoothly from one region to the next. Filaments connect to clusters, clusters connect to other filaments, and voids fill the spaces between. There are no abrupt edges, only gradual shifts in density. This interconnectedness is what holds the cosmos together, not in a physical sense like a solid structure, but through gravitational relationships that have accumulated over billions of years. The cosmic web acts as the framework on which galaxies form, evolve, and drift. Without this web, matter would be distributed evenly throughout the universe, and structures like galaxies and clusters would never have formed. Thinking about our place in this web reveals something both humbling and comforting. We occupy a small position within a vast structure, but that position exists because the universe formed patterns capable of supporting stars, planets, and life. The same gravitational principles that shaped clusters and superclusters also shaped the solar system. The local pattern and the cosmic pattern are connected through the same set of physical laws. Understanding these structures also makes it easier to appreciate how rare it is that we can observe them at all. From Earth, we can only see galaxies that lie within the observable universe. Light from beyond that region has not had enough time to reach us. The cosmic web extends far beyond what we can detect. Our understanding is limited to what light has revealed so far. Yet even within that limitation, the scale remains immense. The observable universe contains hundreds of billions of galaxies, arranged in patterns that stretch across distances so large that the mind eventually stops trying to quantify them and simply accepts their enormity. Much of the universe becomes easier to understand once you realise that most of it is made not of galaxies, stars or planets, but of space itself. This can feel counterintuitive because when we think of the cosmos, we usually picture bright objects, clusters of galaxies, spirals of stars, glowing regions of gas. But those features sit inside an environment where the emptiness far outweighs the matter. The structures we've described, clusters, superclusters, and the cosmic web, are enormous, yet they occupy only a small fraction of the universe's total volume. Once you begin considering the spaces in between, the scale shifts again, stretching beyond anything we have touched so far. These empty regions are often called voids, and the name fits, not because they are literally empty, but because they contain so little compared to the surrounding structures that the term makes sense. A void might span hundreds of millions of light years, but hold only a few galaxies scattered far apart. Trying to imagine these areas can be difficult, because human experience doesn't include anything comparable. On Earth, even the most barren environments still contain life, sound, weather, or terrain. In contrast, cosmic voids contain almost nothing. They are defined not by what they hold, but by what they lack. To picture a void, imagine standing inside a region so vast that you could travel for millions of years without encountering another galaxy. The darkness around you would not be the darkness of night on Earth, which is filled with starlight. It would be something quieter, a region where light from distant galaxies is too faint to brighten the view. The emptiness would feel different, not threatening or dramatic, but expansive in a way that stretches your sense of scale. These spaces are not hostile. They simply exist on a level that far exceeds anything familiar. Even though voids contain little matter, their presence helps shape the universe. The cosmic web forms because gravity pulls matter into filaments and clusters, leaving the lower density regions behind. Over billions of years, the dense regions grow denser, and the empty regions grow emptier. This separation creates the large-scale structure we see today. The existence of voids tells us how matter behaves across vast distances, drifting toward regions where gravity is strongest, and leaving behind expanses where gravity has less influence. Another way to understand the significance of these empty spaces is to consider how they compare to the structures around them. Filaments might contain thousands of galaxies spread across great distances. Clusters might hold even more, but voids often contain almost none. Their size exceeds that of the structures they surround. In some areas, voids stretch across hundreds of millions of light years, dwarfing entire clusters. Considering their size helps emphasize how small the bright structured regions of the universe really are compared to the total volume. What makes these voids especially interesting is that they don't feel empty in the same way a vacuum chamber or a bare room feels empty. They're empty on a cosmic scale, meaning the density of matter inside them is far lower than the universe's average. Gas might still be present, but so thinly that it wouldn't resemble anything familiar. Dark matter may exist there as well, but in smaller amounts than in denser regions. The void's emptiness isn't absolute, it's relative. And relative emptiness at this scale still means a lack so profound that the mind must adjust to comprehend it. Yet these spaces are not entirely isolated. They border the filaments of the cosmic web, forming the negative spaces between the web's strands. Matter flows along these filaments toward clusters and superclusters, leaving the voids even more depleted. This flow happens slowly, shaped by gravity over billions of years. If you could watch the universe evolve from the beginning, you would see small fluctuations in density grow into the large-scale structures we see today. The voids grow larger as the filaments contract and strengthen. The relationship between them reveals how the universe organizes itself without any external guidance. Standing on Earth, it is difficult to sense these structures. When we look at the night sky, the universe appears evenly filled with stars, but that view is limited by our position inside a galaxy. If we could float in intergalactic space, the picture would change dramatically. We would see large regions where galaxies appear only as distant scattered points. And if we floated toward a void, the number of visible galaxies would drop even further until the sky felt almost blank. This contrast highlights how unevenly matter is distributed on cosmic scales. Void regions also help us understand how the universe expands. The expansion of space stretches everything, but it affects voids more noticeably than the dense regions. In clusters, gravity is strong enough to keep galaxies close together despite expansion. In voids, expansion works freely, increasing the distances between the few objects present. Over time, these regions become even more sparsely populated. This difference means the cosmic web becomes more pronounced as the universe ages. Dense regions retain their structure, while empty regions become emptier still. Despite appearing barren, voids have influenced cosmology in important ways. Observations of how galaxies move relative to voids have helped scientists measure the rate of cosmic expansion. Voids act as natural laboratories for studying how matter responds to gravity on large scales. They also help test theories about dark energy, the mysterious force driving the acceleration of the universe's expansion. In this sense, voids play an active role in shaping our understanding of the cosmos, even though they hold so little themselves. Thinking about these empty spaces also offers a new way of interpreting the universe's structure. Instead of imagining the cosmos as filled with objects, it becomes clearer to view it as mostly open space with islands of matter scattered throughout. Galaxies, clusters, and filaments are the exceptions. The rule is emptiness. This perspective helps explain why the universe appears as it does when observed across large distances. The matter we see gathers into patterns not because they fill the universe, but because they emerge from the remaining fraction where matter has accumulated. If the universe were more evenly filled with matter, it might not have formed galaxies or stars at all. The clumps of matter that grew into galaxies required unevenness, small fluctuations that grew over time. Voids are the result of this unevenness. They show how regions that began slightly less dense became increasingly depleted. Without voids, the cosmic web would not exist in its current form. The presence of empty spaces is essential, not incidental. The scale of these voids also helps place Earth's size into a broader context. When thinking about the solar system, Earth appears tiny. Compared to the Milky Way, it becomes even smaller, and when measured against a cluster or supercluster, Earth essentially disappears. But voids are so much larger than even those structures that the solar system becomes negligible in size. These emptier regions stretch wider than anything else we've discussed, extending the sense of cosmic vastness far beyond the boundaries of visible structures. Imagining travelling into a void can help illustrate this scale. You would leave behind regions filled with galaxies and enter a space where the nearest galactic neighbours grow fewer and more widely spaced. As you drift deeper, the galaxies become sparse enough that they no longer form recognisable patterns. The cosmic web fades into the background, and the environment becomes dominated by quiet, open space. The journey would be slow by human perception, but steady on cosmic scales. There would be no sense of crossing a border. The change would occur gradually, with galaxies appearing less frequently until the void's vastness became clear. One misconception people sometimes have about voids is that they must be perfectly empty. But even these regions contain dark matter, cosmic microwave background radiation, and occasional lonely galaxies. They are not complete vacuums. They simply lack the dense formations that define the cosmic web. This relative emptiness is what makes them interesting. They're examples of what the universe becomes in the absence of gravitational attraction strong enough to form structure. Despite their size, voids do not feel like holes in the universe. They are part of the cosmic landscape, as important to its structure as the filaments and clusters. Without them, the patterns we observe wouldn't exist. They act as the negative space that outlines the cosmic web, giving it definition and form. The contrast between dense and empty regions allows the structure to emerge clearly. It's easy to assume that the existence of so many empty spaces should make the universe feel desolate. But that assumption fades when you recognize that emptiness is the backdrop against which all cosmic structures appear. Without these spaces, the clusters and galaxies would not stand out. The emptiness gives scale to everything else, and because space is the dominant feature, the structures within it become even more remarkable. The fact that the universe contains both vast emptiness and intricate structure is what makes it feel balanced. The emptiness is not a flaw or a gap. It's a natural part of how matter spreads out under the influence of gravity and cosmic expansion. The emptiness provides room for galaxies to form, drift, merge, and evolve. Without it, the universe would look very different. Reaching a point where the scale of cosmic voids feels even slightly familiar prepares the mind for the next shift outward, the one that brings us to the limits of what we can actually observe. Everything we've described so far, the solar system, the Milky Way, the local group, the clusters, the superclusters, and the cosmic web, exists within a zone defined not by physical boundaries, but by light. The universe has been expanding for billions of years, and during that time light has been travelling across space, carrying information from distant objects toward us. The farthest regions we can see are those whose light has had enough time to reach Earth since the universe began. This region is what we call the observable universe, and it forms a kind of horizon around us. Not a hard edge, not a wall, but a limit to how far the past can reveal itself. Thinking about this horizon means accepting that our view is shaped entirely by time. Light travels at a constant speed, and the universe has a specific age. The combination of these facts creates a sphere around Earth, roughly 46 billion light-years in every direction, within which all visible cosmic structures reside. It may seem surprising that the radius of this sphere is larger than the age of the universe in years, but expansion explains that. Space itself has stretched while light has been travelling across it, moving galaxies farther away even as their ancient light continues to reach us. This expansion means the observable universe includes regions that are now much farther than the distance their light initially travelled. When imagining this sphere, it helps to picture it not as a physical shell, but as a limit to information. Beyond this horizon, light has not yet had enough time to reach Earth, so we cannot see anything farther away. The objects beyond the horizon are not absent. They simply remain unobserved. Their light is still travelling, slowly making its way across space. If the universe continues expanding and enough time passes, regions now beyond our sight may eventually enter our observable range, while others will drift away faster than light can reach us due to cosmic expansion. The horizon is dynamic, not fixed. It changes as the universe evolves. Visualizing the observable universe is challenging because it encompasses everything we can detect. Every telescope, every observation, every image ever taken fits inside this sphere. Galaxies near the edge look faint and stretched because their light has travelled for more than 13 billion years. These galaxies appear not as they are today, but as they were when the universe was young. Observing them is like looking through layers of time, each layer revealing earlier stages of cosmic evolution. Closer galaxies show us the universe in its more developed state, while galaxies near the horizon show it during its formative period. This time, layering becomes more pronounced when you consider the cosmic microwave background, often described as the oldest light in the universe. It isn't a beam from a distant galaxy. It's a faint glow left over from a time when the universe became transparent to radiation. Before that period, the universe was filled with hot plasma that trapped light, preventing it from travelling freely. When the universe cooled enough, light was able to move across space, and the remnant of that early glow still surrounds us today. This light forms the outermost visible layer of the observable universe. It does not show stars or galaxies. Instead, it shows temperature patterns that reveal how matter was distributed shortly after the universe's expansion began. Understanding this background helps clarify that the observable universe is a snapshot of cosmic history. The farther away we look, the further back in time we see. Light from nearby stars might be only a few years old. Light from distant galaxies might be billions of years old. And the cosmic microwave background captures a moment so early that structures like galaxies had not yet formed. The entire observable universe becomes a record of the universe's evolution from near the beginning to the present. As we imagine moving through this conceptual space, it becomes clear that the universe does not look the same at all distances. Closer regions appear structured, with galaxies, clusters, and filaments forming intricate patterns. Farther regions show simpler arrangements, where galaxies are younger, smaller, and less organized. The outermost regions show only the early distribution of matter, not fully formed structures. The universe evolves over time, and the observable horizon shows different stages depending on how far away we look. One interesting aspect of this horizon is that it surrounds every observer, no matter where they are in the universe. If someone lived in a distant galaxy on the opposite side of this sphere, they would have their own observable universe centered on their location. It would contain many of the same structures, but would also include regions we cannot see from Earth. In this sense, the observable universe is not the universe as a whole. It is simply the region accessible to us based on the finite speed of light and the age of the universe. Recognizing this distinction helps prevent the common misunderstanding that the observable universe marks the true boundary of existence. The actual universe may extend far beyond what we can detect. It may be countless times larger. It may even be infinite. But because light requires time to travel, we see only a portion of it. The rest remains hidden, not because it lacks content, but because its light has not yet reached us. Another factor shaping our view of the observable universe is cosmic expansion. This expansion doesn't push galaxies through space so much as stretch space itself. As space stretches, the wavelengths of light travelling through it stretch as well, becoming longer and shifting toward the red side of the spectrum. This redshift tells us how fast distant objects are receding. By measuring redshift, we can estimate distances and create maps of the observable universe. These maps show the cosmic web, the clusters, the superclusters, and the voids we've discussed, all arranged inside a sphere whose structure becomes less detailed near the edges. As we picture drifting outward toward the horizon, the universe appears to thin. Galaxies become smaller and fainter. Their shapes are harder to distinguish. Clusters are less defined. Eventually, the galaxies blend together into faint smudges as their ancient light struggles to reach us. Beyond that region lies the background glow, smooth and uniform except for tiny differences that reveal the earlier seeds of structure. The journey outward becomes a journey backward in time, tracing the universe from more complex arrangements to simpler beginnings. This perspective also helps explain why Earth cannot observe the present state of distant regions. When we look at a galaxy 10 billion light-years away, we're seeing it as it was 10 billion years ago. Its present form may be entirely different, but the light carrying that information has not yet reached us. This delay does not limit our understanding. It gives us the ability to study the universe's evolution by comparing images at different distances. But it also means that our view is always incomplete. The observable universe shows the past, not a simultaneous snapshot of everything. Despite this inherent limitation, the observable universe still contains an extraordinary amount of structure. Hundreds of billions of galaxies lie within it. Each galaxy contains billions of stars. Many of those stars likely host planets. And the cosmic web ties these systems together across distances so large that even light requires billions of years to cross them. All of this fits inside the visible region, forming a sphere that, while finite, holds more worlds and structures than any one mind can fully grasp. One subtle feature of the observable universe is that it grows over time. As the universe ages, light from more distant regions will eventually reach us. In that sense, our horizon expands. But on the larger scales, cosmic acceleration means that some regions move away faster than light can travel. These regions will eventually slip permanently beyond our ability to observe. The interplay between expanding horizons and retreating structures creates a delicate balance in how much of the universe remains accessible. Thinking about this boundary creates a sense of quiet reflection. The observable universe is enormous, yet it is only a portion of the whole. The regions beyond remain unseen, not because they lack content, but because time imposes a limit on what can be known from one point in space. This limitation is not restrictive. It provides a natural frame for observation, a reminder that every viewpoint in the universe has its own horizon shaped by physics and time. This horizon also emphasizes how small Earth is in the grand scheme. Everything we know, every observation we have made, every measurement, every image from telescopes orbiting Earth, all fit within this sphere. And Earth itself occupies a tiny location near an ordinary star in an ordinary galaxy. That smallness does not diminish our experience. Instead, it highlights the scale of the environment we inhabit. The observable universe surrounds us not as a boundary to be reached, but as a landscape through which light travels to tell us the story of the cosmos. The more we imagine drifting across this landscape, the clearer it becomes that the observable universe is both vast and limited. It shows everything we can see, but not everything that exists. It connects the smallest structures to the largest, yet remains part of an even greater whole. Reaching the edge of the observable universe naturally leads to a question that doesn't arise on smaller scales. What exists beyond what we can detect? Once you understand that the observable universe is defined by the distance light has travelled since the beginning of cosmic expansion, it becomes clear that this limit isn't physical. It doesn't mark the edge of everything. It marks the edge of our information. The regions beyond are not empty or non-existent. They are simply unseen. Thinking about these areas is different from imagining planets or galaxies, because there is no light to guide the picture. Instead, we rely on inference, logic, and the patterns of the visible universe to consider what might lie in the surrounding darkness. The first step in approaching these unseen regions is understanding that the universe likely continues far beyond our horizon. Nothing in the structure of the observable universe suggests it is special or unusual compared to what might exist farther out. The distribution of galaxies appears uniform on large scales. The cosmic microwave background shows near uniformity with small fluctuations. These clues indicate that the universe we can see is part of a larger expanse that shares similar characteristics. If the universe looked drastically different at the edges of the observable sphere, denser in one direction, emptier in another, we might suspect a boundary or change. But the data we have so far suggests continuity. The simplest interpretation is that the universe beyond our sight resembles the universe within it. This idea may sound straightforward, but it carries profound implications. If the universe extends far beyond the observable region, then the number of galaxies exceeds even the staggering counts we've already discussed. The structures of the cosmic web likely continue into regions whose light has not yet reached us. Clusters, filaments, voids, and superclusters may exist in every direction, stretching into a darkness filled not with nothingness, but with hidden content awaiting enough time for its light to arrive. The concept of a universe larger than the observable one doesn't require exotic explanations. It simply follows from the fact that light needs time to travel. Another factor shaping our understanding of these unseen regions is the universe's expansion. Distant galaxies recede from us, not because they move through space, but because space itself expands, carrying them with it. This expansion becomes more pronounced at great distances. In fact, some regions of the universe are receding faster than the speed of light due to this expansion. This does not violate the rules of physics because the galaxies themselves are not moving faster than light. Instead, the space between us and them is stretching. Light from those regions will never reach Earth, because the distance increases too quickly for the photons to close the gap. These regions exist within the universe but permanently outside our observable horizon. Thinking about this creates a distinction between two limits. One is the observable universe, defined by the light that has reached us. The other is the event horizon, defined by the expansion rate beyond which light can never arrive. The observable universe may grow over time as more light reaches us from regions previously too distant. But the event horizon marks a permanent boundary. Anything beyond it is unobservable for as long as the universe continues expanding. This creates a layered sense of distance. Some areas are temporarily unseen but will become visible. Others are permanently out of reach, not because of physical separation, but because space expands too fast for signals to bridge the gap. Despite this limitation, the unseen regions are not mysterious in a supernatural sense. They follow the same physical laws we observe locally. The patterns we've studied, the cosmic web, the distribution of galaxies, the temperature fluctuations of the early universe, point toward a consistent set of rules governing the cosmos. This consistency allows us to make reasonable assumptions about what lies beyond. If the visible universe contains clusters and voids, the unseen regions likely contain them too. If galaxies form stars in predictable ways within our horizon, they likely do so outside it. The darkness beyond observation becomes a continuation rather than a break. A related idea emerges from the notion of cosmic inflation, the rapid expansion theorized to have occurred in the earliest moments of the universe's existence. According to inflationary theory, space expanded exponentially, smoothing out irregularities and stretching tiny fluctuations into the seeds of today's cosmic structure. If inflation occurred, the universe must be far larger than the observable region. The inflationary process would have expanded space to such an enormous extent that even a fraction of it visible to us today would represent only a tiny patch of a much larger whole. This perspective shifts the mind away from thinking of the observable universe as a large place. Instead, it becomes a small window into something significantly greater. Some versions of inflationary theory even propose that the universe might be infinite. An infinite universe would not require unusual properties or exotic shapes. It could simply mean that space extends without boundary in all directions. In that case, the observable horizon becomes a local limit rather than any kind of edge. Beyond it, space continues indefinitely, containing more galaxies than can ever be counted. Whether or not the universe is truly infinite, the possibility underscores that what we see is only a portion of a larger expanse. It's also possible that regions beyond our horizon differ slightly from the observable universe. Over extreme distances, variations in density or composition might exist, but these differences would need to be consistent with the overall uniformity observed locally. If there are areas where cosmic structures appear thicker or thinner than what we observe, their differences would be gradual rather than abrupt. The laws of physics would still apply. Gravity would still shape matter. Light would still follow the same rules. Even if the universe contains subtle variations, these variations would arise from the same underlying framework. Another question arises when considering regions beyond observation. Could there be other civilizations, other planetary systems, or entirely different arrangements of galaxies? Based on what we know, nothing limits these possibilities. If the universe outside our horizon mirrors the observable region, then countless galaxies exist beyond our view. Many of those galaxies would contain stars. Many stars would host planets. Whether any of these planets harbour life is unknown, but the scale alone suggests the potential is vast. The darkness beyond our sight is not empty of worlds, it is simply empty of light reaching us from them. This thought does not require speculation about unfamiliar laws of nature. It simply extends the patterns we already observe. If life developed on Earth around an ordinary star in an ordinary galaxy, then similar conditions might exist elsewhere, both within and beyond the observable universe. Distance alone does not limit the possibility. It only limits our ability to detect it. When reflecting on what lies beyond observation, it becomes clear that the universe's unseen regions are not mysterious because they are chaotic or unpredictable. They are mysterious because they remain inaccessible for now. Their contents follow the same laws shaped by the same forces, evolving along the same paths that produce the structures we can see. This continuity is reassuring. It means that even the unseen follows a familiar logic. Thinking about these possibilities changes how we view the observable universe. Instead of treating it as everything, it becomes the portion of the cosmos we have access to because light has travelled long enough to reach us. Beyond it lies the continuation of the universe's large-scale structure. In this sense, the horizon becomes a boundary imposed by time rather than a limit to existence. Another layer emerges when considering the future of the observable universe. As cosmic expansion continues, distant galaxies will move beyond the event horizon. Over very long timescales, only the galaxies gravitationally bound to the Milky Way, those in the local group, will remain visible. Everything else will fade from observation. Structures that currently shape our view of the universe will slip into darkness, not because they disappear, but because their light can no longer reach us. Meanwhile, regions now unobservable might become visible if their light arrives before expansion carries them beyond the horizon. The observable universe is dynamic, constantly shifting as time passes. This dynamic nature doesn't impose any kind of urgency. The changes occur on scales so large that entire civilizations could rise and fall before any noticeable difference emerges. Instead, the shifting horizon emphasizes that the universe is always evolving, even on the largest scales. The boundary of observation is part of that evolution, a reminder that knowledge grows as more light reaches us, while limitations arise as expansion carries information away. Thinking about what lies beyond observation also introduces an idea often discussed in cosmology: the possibility of regions where conditions might differ slightly because of how inflation unfolded. If inflation occurred unevenly in extremely distant regions, there could be areas where densities vary slightly, or where certain physical constants differ by small amounts. These differences would not be dramatic changes in the laws of physics, but subtle shifts in conditions. They would be far beyond our observable range, making them part of the universe we infer rather than the universe we see. Exploring these possibilities doesn't require imagining anything outside the laws of physics. It simply recognizes that the universe might be large enough to contain variations arising from early differences stretched across great distances. Whether these variations are significant or negligible is unknown, but the idea demonstrates how little of the total universe we can currently observe. In considering these unseen regions, it becomes helpful to imagine the observable universe as a kind of spotlight illuminating a small portion of a vast stage. The stage extends far beyond the lit area, but the spotlight reveals only a local region. The darkness around it is not empty. It is simply unlit. The contents of the darkness follow the same rules as those within the lighted region. The spotlight expands slowly as more light reaches us from distant parts of the stage, but the stage itself may be far larger than what we will ever see. This perspective makes the observable universe feel both vast and modest. Vast because it contains more stars, galaxies, and structures than the mind can comfortably visualize. Modest because it may represent only a small fraction of the total cosmos. The unseen regions do not diminish the significance of what we can observe. They broaden it. They remind us that the universe's richness extends far beyond our current detection. Thinking about the universe in this way reveals a comforting truth, that the cosmos does not end where our vision fades. Beyond what we can see lies the continuation of the same structures, shaped by the same forces, following the same patterns. The darkness is not a void in the usual sense. It is an area where light has not yet arrived. It holds possibilities consistent with what we already know, extending the familiar into distances we cannot measure with direct observation. When you follow the universe outward far enough to feel comfortable imagining regions we cannot see, an interesting question starts drifting back toward the foreground. If all of this exists, if the solar system is small, if the galaxy is vast, if galaxies form clusters, if clusters form superclusters, and if all of that rests inside a cosmic web that stretches into regions beyond our visibility, then where does Earth fit in terms of size? The question is simple, but answering it requires comparing Earth not only to nearby objects, but also to the entire chain of scales we've been travelling through. The result is a perspective that doesn't diminish Earth, but reshapes how we perceive the meaning of small and large. One way to begin is to return for a moment to something familiar. Earth feels big from the surface. Oceans stretch beyond sight. Continents require hours or days to cross. Mountains rise high enough that climbing them becomes an accomplishment. Yet these impressions come from living at ground level. The size we feel is not the size the universe sees. If you were to move just a small distance above Earth, far below the height of satellites, you would already notice the planet rounding beneath you. The horizon curves, the surface becomes a sphere, and the details that once felt enormous blend into a single surface. At this scale, Earth begins to feel contained, not insignificant, but finite in a way that the surface never suggests, and that containment becomes more apparent with each additional step outward. The moment you place Earth next to the Moon's orbit, the scale shifts again. The average distance to the Moon is so large that dozens of Earths could line up between the two bodies with room to spare. Suddenly the planet that once felt vast fits comfortably inside a region of space that the human mind rarely considers on a daily basis. Expanding this comparison further, the orbit of Earth around the Sun adds another layer. Earth's entire orbital path would look modest compared to the size of the Sun if the distances were scaled proportionally. Even though the Sun appears compact from a distance of 150 million kilometres, its mass and volume dwarf Earth's by enormous factors. You could fit over 1 million Earths inside the Sun. If Earth were the size of a grain of sand, the Sun would be a sphere large enough to fill a room. This comparison often brings the first genuine sense that Earth is small, not because it lacks substance, but because the solar system around it is so much larger. Yet even the Sun, impressive as it is, becomes modest when compared to the solar system's total span. The region influenced by the Sun's gravity extends far beyond the orbits of the planets. Comets in the distant Oort cloud orbit so far away that their paths take thousands or even millions of years to complete. If Earth's orbit were a small circle drawn on a sheet of paper, the Oort cloud would extend far beyond the edges of the page. The solar system's size makes Earth look like a point inside a wide, quiet expanse. When you continue upward in scale and consider the Sun's place within the Milky Way, the comparison grows even more dramatic. The entire solar system fits so comfortably in a tiny part of the galaxy that it becomes almost impossible to represent both accurately on the same diagram. The Milky Way spans about 100,000 light-years across. The solar system is less than a light-year in diameter, if you measure out to the very distant reaches where the Sun's gravitational influence fades. Earth's orbit is just a fraction of that fraction. It becomes a dot within a dot inside a structure so large that human senses cannot relate to it directly. This is not a matter of perspective or exaggeration. The numbers themselves confirm it. If the Milky Way were reduced to the size of a large continent, the solar system would be smaller than a single grain of dust on that continent. Earth would be a particle of that dust. From this vantage point, Earth begins to look truly small, not diminished, not unimportant, but one tiny member of a vast stellar population that fills a galaxy stretching farther than any single lifetime could ever grasp. As the comparisons continue, the sense of scale expands again when galaxies are placed in clusters. The Virgo cluster, containing thousands of galaxies, stretches across millions of light-years. Each galaxy inside it contains billions of stars. Each star may host planets. Earth becomes a small world orbiting a single star in a galaxy that is merely one among thousands in a cluster that itself is only one part of a much larger arrangement. the numbers increase so quickly that they stop feeling like quantities and begin to feel like steps in a scale that grows steadily outward. The step from clusters to superclusters amplifies this effect. The Virgo supercluster contains the local group, which holds the Milky Way, and countless other groups spread across a space hundreds of millions of light-years across. Earth's place in this structure becomes almost invisible, not because Earth holds no interest, but because the scale stretches too far for individual worlds to register when placed against the full span of these structures. Even the Milky Way, impressive on its own, becomes a small feature of a larger region. Continuing outward into the cosmic web, the structures become even larger. Filaments span hundreds of millions of light-years. Voids stretch between them with sizes so large that the Milky Way could cross some of them and still appear tiny within their central emptiness. Earth does not diminish further, because it is already smaller than what the scale can effectively represent. Instead, the structures around it grow so vast that Earth's size becomes no more or less significant than a single pixel inside an enormous image. This change in relative scale does not erase the meaning of Earth. It simply places it within a larger context. Moving outward beyond the cosmic web to the scale of the observable universe brings additional perspective. The observable universe spans about 93 billion light-years in diameter. This distance reflects how far light has travelled after billions of years of expansion. Within this sphere lie all the galaxies we can detect, all the clusters, all the filaments, and all the voids. Earth occupies a location near one star in one galaxy, near the edge of one filament inside a structure so large that even the Virgo supercluster occupies only a tiny fraction of it. This perspective often prompts a question. Does Earth become irrelevant when placed against such vast structures? The answer lies in understanding how scale works. Earth is small physically, but size does not dictate relevance. The universe contains objects so large that they overshadow entire galaxies, yet that doesn't give them more inherent meaning than a small planet capable of supporting life. The purpose of these comparisons is not to make Earth seem insignificant, but to clarify that physical scale differs from experiential significance. Earth matters profoundly to the beings who live on it. Its small size simply reflects the fact that the universe has room to contain structures of many different scales. What often surprises people when they consider Earth's size in this context is how quickly the scale shifts from familiar to incomprehensible. The progression from Earth to the solar system feels manageable. The leap from the solar system to the galaxy stretches understanding. The jump from the galaxy to the observable universe often requires a different mode of thinking. At this level, scale becomes something the mind navigates through analogy, rather than direct visualization. Earth becomes part of a structure that grows so far beyond intuitive human experience that describing it accurately requires careful mental steps. Another perspective that helps clarify Earth's relative size is to think of how much the planet influences its surroundings. Earth's gravitational pull affects only nearby objects on a scale of planetary distances. The Sun's gravity dominates the solar system. The Milky Way's gravity shapes the motions of billions of stars. Galaxy clusters influence enormous volumes of space. On this scale, Earth's gravitational influence is extremely localized. It shapes its immediate environment, holds the Moon in orbit, and governs the movement of satellites. But beyond that small region, its influence fades quickly. Yet despite this physical smallness, Earth stands out because of what happens on its surface. It is the one environment we know that hosts life. It contains landscapes, oceans, weather patterns, and ecosystems. It is the only place where consciousness has been observed. These qualities introduce a different dimension that is not measured in kilometres or light years. Earth is small physically but immense in complexity. In terms of structures that hold life, it is not dwarfed by larger objects. Size does not determine intricacy or depth of experience. Another way to think about Earth's size is to place it within the timeline of cosmic evolution. The universe has existed for about 13.8 billion years. Earth formed around 4.5 billion years ago. Life began early in Earth's history and evolved over billions of years. The planet's timeline occupies a substantial portion of the universe's total history. This longevity emphasizes that size alone does not determine a cosmic object's importance. A world can be small and yet host long, complex stories that unfold over enormous stretches of time. Thinking about how Earth compares to everything else also highlights an interesting truth. Much of the universe consists of empty space. When comparing sizes, it becomes clear that Earth is small compared to astronomical distances. But galaxies, clusters, and the cosmic web themselves occupy only a small fraction of the volume of the observable universe. Most of space is empty. Earth is small in a landscape dominated by emptiness. That emptiness doesn't diminish Earth. It simply reinforces that matter occupies only a small portion of the cosmic expanse. Considering Earth in this context does not require imagining anything mystical or unusual. It simply involves scaling familiar objects into larger structures. Earth becomes small compared to the solar system. The solar system becomes small compared to the Milky Way. The Milky Way becomes small compared to the observable universe. And the observable universe becomes only a portion of a possibly larger cosmos. Earth's size is real, but its meaning depends on perspective. Once you become comfortable with this comparison, the idea of small begins to shift. Earth is small physically, but size is only one way of describing something. Earth is large enough to host continents, oceans, life, and the entire history of human civilization. It is large enough to generate weather patterns, to sustain ecosystems, and to maintain a complex atmosphere. It is large enough to act as a home. What matters is not the physical size, but the role it plays within the experiences of those who live on it. Another aspect worth noting is that Earth's smallness makes the universe easier to explore conceptually. The scale grows upward in steps that allow each level to feel distinct. Earth is small. The solar system is larger. The galaxy is larger still. The cosmic web is larger than that. Each step upward introduces new structures without overwhelming the mind all at once. Earth's small size provides a starting point from which the mind can expand outward gradually. This transition from Earth to the cosmos doesn't diminish the planet. It enhances understanding. Earth becomes the reference point for comparisons that stretch outward into ever larger scales. And as we continue to move outward in this mental journey, another question begins forming. If Earth is small compared to everything else, then how does time behave across these scales? After spending so much time moving outward from Earth, through the solar system, across the Milky Way, through clusters, superclusters, voids, and the observable universe, a curious feeling often emerges. The universe seems impossibly large, almost beyond what thought can comfortably hold. Yet at the same time, something about it feels connected in a way that doesn't overwhelm. There is a sense that everything, despite its scale, belongs to the same quiet arrangement. The distances are enormous, but the structures behave in ways that link them together. The universe feels vast, but also strangely unified, as if every part participates in a shared pattern. This sense of connection becomes clearer when you revisit the steps you've taken along the journey. Each scale introduces new sizes, new structures, and new forms of organization, but none of them exist in isolation. Earth orbits the Sun. The solar system orbits the center of the Milky Way. The Milky Way belongs to a group of galaxies. The group belongs to a cluster. The cluster sits in a supercluster, and the supercluster occupies a position in the cosmic web. Even the cosmic web fits into the observable universe, and the observable universe itself sits inside a larger region shaped by the laws of physics. No matter how large the scale becomes, every part remains connected to the others through shared processes. Understanding this connection requires thinking about the forces that shape the universe. Gravity, for example, acts everywhere. It pulls objects together on every scale. Planets orbit stars, stars orbit galaxies, galaxies orbit within clusters, and clusters drift within superclusters. Even the large-scale structure of the cosmic web forms because gravity amplifies tiny variations in density over billions of years. This single force links everything from the fall of an object on Earth to the orbits of galaxies across millions of light-years. The scale changes, but the underlying process remains consistent. Light provides another kind of connection. Every star shines across space. Every galaxy emits light that travels through the universe. Light carries information from one region to another. It reveals distances, shapes, motions, and histories. When you look at a star, you're seeing an object that may be dozens or hundreds of light years away, yet its light reaches your eyes effortlessly. When you look at a galaxy through a telescope, you're seeing something millions or billions of light years distant, connected to you only because light has managed to cross that space. The universe feels vast because of the distances involved, but it feels connected because light moves through that space and brings information with it. The cosmic microwave background adds another layer to this connection. It is light that fills all of space, left over from an early moment when the universe became transparent. Every point in the observable universe receives this faint glow. No matter where you look, the background remains. It ties everything together by offering a shared history. Every galaxy, every cluster, and every region of the cosmic web formed within the same expanding environment that once glowed much more brightly. The background light is a reminder that the universe was once far simpler before expanding into the complexity we now observe. The expansion of the universe itself also creates a quiet sense of unity. Space stretches everywhere at once. Galaxies drift apart not because something pushes them individually, but because the fabric of space expands uniformly. This expansion affects every region, no matter how far away. It ties all cosmic structures into one evolving continuum. The universe feels enormous because it continues stretching, but it feels connected because that stretching happens throughout its entirety, not in isolated pockets. Another reason the universe feels both large and unified is that the patterns repeat across scales. On Earth, matter forms into familiar structures: mountains, oceans, continents. In space, matter also gathers into structures, though much larger: stars, planets, nebulae, galaxies. These structures form because the same principles apply everywhere. Gas collapses under gravity. Stars ignite in dense regions. Matter clumps together over time. Galaxies form spiral arms or elliptical shapes depending on their history. Clusters emerge where many galaxies form close to one another. The repetition of these processes across scales creates a sense of continuity. You may be looking at structures millions of light years apart, but they arose from the same kinds of physical rules. Time adds another dimension to this feeling. Everything in the universe evolves according to similar processes of change. Stars are born, live, and die. Galaxies merge, grow, or fade. Clusters gather more galaxies or slowly drift apart. Superclusters shift across space. Even the cosmic web evolves over billions of years as matter streams along filaments. These processes occur slowly, but they create a shared rhythm. Earth's history fits into this rhythm. The planet formed from a cloud of gas and dust around a young star. The star formed from a collapsing region inside a larger gas cloud within a spiral arm of the Milky Way. The galaxy formed from earlier generations of stars. The chain stretches all the way back to the beginnings of cosmic structure. This continuity allows Earth to feel part of the universe, even though Earth is tiny by comparison. The atoms in rocks, oceans, and living beings originated in stars that lived and died long before the sun formed. Elements heavier than helium were created in earlier generations of stars or in supernova explosions and then scattered across space. Those elements became part of later stars and planets. The universe feels vast because the distances and timescales are enormous, but it feels unified because everything shares a common origin in earlier cosmic processes. Another factor contributing to this sense of connection is the structure of space itself. The universe does not contain pockets of unrelated physics. The same laws govern every region we've been able to observe. Gravity behaves the same way in distant galaxies as it does in the solar system. The behaviour of atoms remains consistent. Light follows the same patterns. This uniformity creates a sense that the cosmos is not a patchwork, but a continuous whole. Even voids, which at first seem like disconnected gaps, contribute to the universe's unified structure. They are not random holes, but predictable parts of the cosmic web. They form because matter gathers along filaments, leaving behind lower density regions. These voids stretch and expand along with the rest of the universe. Their shapes change gradually as the web evolves. They may feel empty, but they are part of the same large-scale pattern that includes the densest clusters. The emptiness emphasizes the presence of the structures around it, making the cosmic web more distinct. Another way the universe remains connected is through motion. Nothing is truly still. The Earth rotates and orbits the Sun. The Sun moves through the Milky Way. The Milky Way moves through the local group. The local group drifts toward the Virgo cluster. The Virgo supercluster moves within the Laniakea supercluster. All of these motions follow predictable gravitational influences. Even though the distances are vast and the motion appears slow from our perspective, everything participates in a broader cosmic flow. The idea that every object from planets to galaxies drifts through space as part of a larger movement creates a sense of continuity. When thinking about the universe as a whole, it becomes useful to recognize that connection does not require physical proximity. Earth is far from most stars, yet starlight reaches us. The Milky Way is far from other galaxies, yet gravity influences their motions. Clusters are far from one another, yet they align along filaments shaped by early fluctuations. The observable universe is enormous, yet every point within it originated from the same early expansion. These connections do not shrink the universe. They allow its vastness to feel coherent. Another aspect of this coherence comes from how we study the universe. Observations from telescopes reveal distant galaxies that behave similarly to nearby ones. Physics experiments show that fundamental properties remain constant across space. These consistencies give us confidence that the universe functions according to rules that apply everywhere. The cosmos becomes less intimidating when you realize that familiar principles guide even its largest structures. This sense of unity becomes more pronounced when you consider how the universe's history unfolds. The early universe was simpler, with matter distributed more evenly. Over time, small irregularities grew into the structures we now observe. These irregularities became galaxies, clusters, and the cosmic web. Everything we see today evolved from the same starting conditions. This shared origin means that all matter is related through time. Even objects billions of light-years apart share a common beginning. When imagining the universe on a human timescale, it can feel static. Stars appear fixed in the night sky. Galaxies seem unchanging. But on cosmic timescales, everything flows. Stars are born and die. Galaxies collide and merge. Clusters shift. The cosmic web stretches. This motion creates a sense that the universe is not fixed, but living in a quiet, ongoing transformation. Earth participates in this transformation, even if human lifespans are too short to notice these changes directly. The feeling that the universe is both vast and connected also arises from how easily we can represent its larger structures in simplified forms. When astronomers map the positions of galaxies, the patterns become visible. Filaments, clusters, and voids appear across the map. These structures look organized, not chaotic. The universe forms patterns naturally, not through intention, but through the combined effects of gravity, expansion, and time. When viewed this way, the cosmos feels like a continuous environment rather than a collection of disconnected objects. Another reason the universe feels connected is that no region exists in total isolation. Even in voids, background radiation permeates space. Gravitational interactions extend across great distances. Expansion affects all regions uniformly. The universe is not segmented into unrelated domains. It is a single, continuous entity with varying densities and structures. This continuity provides a sense that no matter how far apart two regions lie, they still belong to the same overarching environment. Perhaps the most comforting aspect of this connection is that humans can perceive it at all. From a small planet orbiting an ordinary star, people have mapped galaxies billions of light years away, measured cosmic expansion, detected the faint glow from the early universe, and traced the structure of the cosmic web. These achievements reveal that the universe's laws allow small beings on a small world to understand patterns on the larger scales. This capability reflects a deeper connection. The mind that observes the universe is made of the same matter shaped by the same processes that formed stars and galaxies. In this way, Earth does not feel separate from the universe, even though it is tiny compared to the structures around it. It feels like a point inside a wider pattern, connected by physics, history, and the flow of time. The universe is vast because distances and scales stretch far beyond everyday experience. But it is comforting because it behaves consistently, evolves coherently, and includes every region within a unified framework. As this sense of unity becomes clearer, another question begins forming in the background. If the universe itself is vast yet connected, what does this suggest about where our journey leads next? After moving so far outward, through scales that stretch from the familiar to the nearly unimaginable, a natural impulse begins to pull the mind inward again. It doesn't erase the vast structures we have passed, or diminish the sense of distance we have grown accustomed to. Instead, it creates a feeling of wanting to see everything again from the viewpoint where it all began. The idea of returning to Earth isn't a reversal of perspective, it's a way of threading all the scales together, understanding how the smallest point in our journey relates to the largest. The return is gentle because nothing in the universe demands urgency. Every part of it moves on timescales that outlast entire civilizations. In that quiet stretch of time, there is room for the mind to drift back toward the little world that started the question of scale in the first place. As soon as you start imagining this inward path, something becomes clear. Earth hasn't grown any smaller or larger during the journey. It hasn't changed in size or shape, simply because you've compared it to galaxies and clusters. The change happens entirely in perception. When your viewpoint expands to include structures larger than anything the senses can grasp directly, Earth appears tiny. Yet when you approach again, down through the layers of scale, the familiar details return. Oceans, continents, atmosphere, and life all re-emerge as features that matter, not because they are large or small, but because they are home. The idea of home becomes easier to appreciate after you've imagined the universe at its largest. Stars and galaxies fill the cosmos, but none of them hold the specific patterns of soil, weather, water, and life that Earth does. The return begins by recognizing that no matter how vast the structures beyond Earth grow, the planet maintains a unique role for those who live on it. Its environment developed over billions of years. Its atmosphere evolved to support complex ecosystems. Its surface contains everything humans have ever experienced, discovered, built, or imagined. The scale of the universe does not erase these facts. It simply places them into a broader context. As you begin to step back toward the Milky Way, Earth becomes a distant point again, not because it shrinks, but because the surrounding structures overshadow it. The spiral arms, the star clusters, the diffuse glow of star-forming regions, all of these features fill the galactic environment with distances that dwarf the width of the solar system. Yet Earth remains in place. orbiting the Sun at the same steady pace it has kept for billions of years. Its size does not matter to the galaxy, but its role matters to the beings who consider it home. This distinction becomes comforting rather than overwhelming. The universe operates on one set of scales, while life on Earth operates on another. Continuing inward, the galaxy no longer fills the view. The cosmic web fades, first into filamentary structures, then into clusters, and finally into individual galaxies. As each layer recedes, the enormity of the universe doesn't disappear. It simply becomes a background for the smaller scales. This transition mirrors the way human perception works. When standing on a mountain, the horizon feels wide. But when walking through a forest, the horizon narrows and the details become immediate. Neither perspective is wrong. Each reveals something different about the world. The universe behaves the same way. When viewed at its largest, it becomes a network of galaxies. When viewed from Earth, it becomes a sky full of stars. Moving farther inward, past the boundaries of superclusters, the structures grow familiar again. The Milky Way reappears not as one point among many, but as a coherent spiral galaxy. The Sun becomes one of its stars. Earth becomes one of the planets orbiting that star. This sequence of reappearing structures doesn't undo the enormity of what lies beyond. Instead, it reinforces the idea that each scale has its own logic. Earth fits comfortably into the solar system. The solar system fits into the galaxy. The galaxy fits into the cosmic web. Nothing needs to be large or small across every scale to be meaningful within its own framework. As the journey narrows further, the solar system becomes the immediate environment again. The orbits of the planets form a pattern that is both simple and stable. The Sun's gravity shapes everything around it. Earth orbits predictably, keeping a distance that allows liquid water to exist and life to flourish. From this distance, Earth becomes visible as a sphere, blue and white when sunlight reflects from clouds and oceans. This view doesn't diminish the planet's size. It highlights the presence of an environment capable of supporting complexity on a scale that doesn't require comparison to galaxies to be significant. Descending closer still, the atmosphere becomes visible as a thin layer surrounding the planet. This layer is small compared to Earth's radius, yet it contains the air that supports life. The thinness of the atmosphere often surprises people when seen from afar, but thin does not mean fragile. It has persisted for billions of years, shaped by volcanic activity, biological processes, and the sun's radiation. Seeing it from this vantage point highlights how much Earth's environment depends on delicate balances that unfolded over long spans of time. Continuing downward, the planet's surface reappears. Land masses, oceans, deserts, forests, and ice become visible again. These features, invisible from the scale of galaxies, now fill the entire field of view. The familiar shapes of continents return. The patterns of clouds drift across the atmosphere. Rivers carve through land. Waves form and dissolve. Weather patterns shift. These details are infinitely more complex than the structures of clusters or superclusters. They change daily, hourly, minute by minute. This complexity reminds you that size is not a measure of dynamism. Earth may be small compared to the universe, but its surface is alive with continuous movement. As the return continues, the details become even finer. Cities appear, mountains rise, forests spread, the textures of landscapes become visible. These features are small in the global sense, but significant within the scale of daily life. The ground beneath your feet, the air you breathe, the sounds of weather, the changing of seasons. None of these require comparison to cosmic distances to possess meaning. They are part of the immediate experience that defines life on Earth. Thinking about the return in this way reveals something subtle. The universe may be large, but it does not erase the significance of smaller scales. The structures beyond Earth give context, not competition. Earth's place in the universe is not diminished by its size. It is framed by it. The journey outward shows how much space exists beyond what we see each day. The return inward shows how many layers of complexity exist within the world we inhabit. These two perspectives complement each other rather than conflict. Another part of this return involves recognizing that Earth is not isolated from the universe. The planet formed from material produced in earlier generations of stars. The atoms in the ground, the atmosphere, and living beings all originated in processes that unfolded in the galaxy long before Earth existed. This connection tightens the sense that Earth belongs to the universe, even if its size is small compared to the larger structures. The materials that make up Earth come from stars. The energy that drives life comes from the sun. The cycles of tides, seasons, and climate arise from interactions with the moon and the sun. Earth is both small and deeply connected to the larger cosmos. Continuing inward, the personal scale becomes the focus. The details of daily life return. Homes, roads, plants, animals, humans, and all the interactions between them become visible again. None of these features appear from the viewpoint of the cosmic web, yet they are part of the same universe. The scale shifts dramatically, but every object, from a human cell to a galaxy cluster, exists within the same physical reality. This connection is not metaphorical, it is literal. The laws of physics governing galaxies are the same laws that allow molecules to form and life to develop. This transition from cosmic scale to human scale creates a kind of grounding. The vast distances and enormous structures do not overwhelm when placed alongside the immediate details of life. Instead, they offer a broader perspective. Earth feels small when compared to the universe, but the universe feels more understandable when approached from Earth. The two perspectives reinforce each other. The large-scale structure provides context. The small-scale experience provides meaning. As the return continues, something else becomes clear. The reason Earth feels like home is not simply because of size or scale. It is because everything humans know, every memory, every story, every discovery, has taken place on or near this planet. The smallness of Earth in physical terms does not diminish its role in human life. The universe contains enormous structures, but none of them replace the meaning of standing on solid ground, feeling air move across the skin, or watching light change through a day. This recognition does not require ignoring the vastness of the universe. It integrates it. Earth is part of this larger structure, not separate from it. The journey outward reveals the scale of the universe. The journey inward reveals the depth of Earth's complexity. Together they create a balanced understanding of place. Earth is small, but it is not lonely. It fits into a universe filled with patterns that support its existence. It participates in a chain of structures that stretches from the smallest particles to the largest cosmic formations. Reaching the final steps of this inward return, the planet feels familiar again. The sounds of weather, the movement of water, the presence of life in countless forms. These details do not contradict the vastness of the universe, they coexist with it. Earth is one expression of the universe's ability to organize matter into complex patterns. Its size does not limit its significance. Its scale does not define its value. It is one world among many, but for those who live on it, it is the world that makes everything else understandable. And as you settle back into the view of Earth not as a dot among galaxies, but as the immediate environment beneath your feet, the sense of scale gained from the journey remains. The universe stays vast, Earth stays small, but the connection between the two becomes clear in a way that feels steady and grounded, not overwhelming. The return doesn't close the journey. It simply brings the perspective back to the place where questions naturally begin, leaving room for curiosity to continue unfolding in whatever direction the mind chooses next.